Any theory, no matter how elegant or beautiful, must ultimately stand the test of experimental verification. Einstein, for his part, identified several potential experiments that could prove or disprove his ideas. The first of these involved the curious orbit of Mercury. When astronomers calculated the planet's movement, they noticed a slight anomaly. Instead of following a perfect ellipse as Newton's equations predicted, Mercury exhibited a peculiar shift, tracing out what looked like petal-shaped paths. To defend Newton's laws, astronomers hypothesized the existence of a new planet, which they named Vulcan, orbiting inside Mercury's path. They argued that Vulcan's gravity was subtly disturbing Mercury's orbit. This strategy had previously led to the discovery of Neptune, but despite their efforts, no empirical evidence for Vulcan was ever found. Using his own theory of gravity, Einstein recalculated Mercury's perihelion, which is the point of its closest approach to the Sun. He found a slight deviation from Newton's predictions. He was absolutely ecstatic when observational data proved to match his calculations perfectly. Specifically, Einstein calculated that the precession of Mercury's orbit, which Newtonian gravity couldn't explain, should be 42.9 arcseconds per century. This figure, remarkably, fit perfectly with the experimental observations. He later recalled with fondness, "For several days I was beside myself with joyous excitement. My wildest dreams had come true." Furthermore, Einstein realized that according to his theory, the Sun ought to deflect light. He understood that the Sun possessed sufficient gravity to bend the path of starlight from stars appearing close to it in the sky. Since these stars are only visible during a solar eclipse, Einstein proposed sending an expedition to observe the 1919 eclipse, specifically to test his theory. Astronomers were tasked with taking 2 photographs of the night sky, one when the Sun was absent, and another during the solar eclipse itself. Comparing these 2 images would then reveal that the apparent positions of the stars had shifted due to the Sun's gravity. Einstein was utterly convinced that the observations would confirm his theory. When asked what he would think if the experiments failed to confirm his theory, he famously replied, "Then I would feel sorry for God, for the theory is correct." Einstein was so confident, in fact, because, as he wrote to his colleagues, his theory possessed magnificent mathematical beauty and symmetry. Ultimately, the renowned astronomer Arthur Eddington carried out this phenomenal experiment, and his results wonderfully matched Einstein's prediction. Today, the bending of light by gravity is regularly put to practical use by astronomers. As starlight passes near a distant galaxy, it bends as if passing through a lens. This phenomenon is known as a gravitational lens, or sometimes an Einstein lens. In 1921, Einstein was awarded the Nobel Prize. Soon after, he became one of the most famous people on the planet, surpassing most movie stars and politicians in renown. In 1933, he even appeared alongside Charlie Chaplin at a film premiere. Both celebrities were immediately surrounded by fans clamoring for autographs. Einstein, quite puzzled, asked Chaplin, "What does all this mean?" Chaplin replied, "Nothing. Absolutely nothing." And then added, "They cheer me because everyone understands me. They cheer you because no one understands you." Of course, a theory that overthrew Newtonian physics, which had reigned supreme for 250 years, was bound to provoke fierce criticism. One prominent skeptic leading the charge against it was Columbia University professor Charles Lane Poore. Upon reading about the theory of relativity, he scoffed, "I feel as if I've been wandering with Alice in Wonderland and having tea with the Mad Hatter." However, Max Planck was always there to encourage Einstein. He famously wrote, "A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it." For decades, attacks on the theory of relativity recurred, but each time, Einstein's theory successfully passed scrutiny. Ultimately, Einstein's theory of relativity transformed all of physics, sparking a true revolution in our understanding of the universe, its origin, and its evolution. It also profoundly changed our way of life. One compelling confirmation of Einstein's theory, perhaps surprisingly, can be found in the global positioning function of your mobile phone. The GPS geolocation system relies on 31 satellites in Earth's orbit. At any given moment, your mobile phone can receive signals from 3 of these satellites. These 3 satellites travel along different trajectories and are positioned at varying angles relative to you. Your phone's processor then analyzes the data received from these 3 satellites and, using triangulation, pinpoints your exact coordinates. The GPS system is so precise that its calculations must account for tiny corrections dictated by both special and general relativity. Because these satellites travel at speeds of roughly 27,500 kilometers per hour, their clocks run slightly slower than those on Earth. This is due to the effects of special relativity, which states that time slows down at high velocities. This phenomenon is illustrated by Einstein's famous thought experiment involving an attempt to outrun a light beam. However, as gravity weakens the further you move into outer space, time actually speeds up slightly. This is in accordance with general relativity, which posits that gravity warps space-time. The weaker the gravitational pull, the faster time progresses. This means that special and general relativity exert opposing effects. Special relativity causes signals to slow down, while general relativity causes them to speed up. Your mobile phone accounts for both of these effects to tell you your precise location. So, without the coordinated interplay of both special and general relativity, you'd simply be lost. Newton and Einstein were, in essence, polar opposites. Although Einstein was hailed as the new Newton, their fundamental characters stood in stark contrast. Newton was a recluse, deeply introverted to the point of being antisocial. He had no close friends and completely struggled with simple everyday conversation. Physicist Jeremy Bernstein once said, "Anyone who had the opportunity to spend enough time with Einstein came away with an overwhelming sense of the man's nobility." When you think of him, the epithet humanity comes to mind again and again, symbolizing the simplicity and attractiveness of his character. And yet, despite these stark differences, Newton and Einstein shared several common traits. The first of these was their extraordinary ability to focus and to marshal immense mental energy. Newton, for instance, when deeply absorbed in a problem, might forget about food and sleep entirely. He could pause mid-conversation and start writing on whatever was at hand, sometimes even on a napkin or a wall. Einstein, similarly, could work intensely on a single problem for several years or even decades. While developing his general theory of relativity, he was reportedly on the verge of a nervous breakdown. Another shared quality was their ability to visualize problems through diagrams. Newton, for example, could have written his Principia solely using algebraic symbols. Instead, he filled his masterpiece with geometric diagrams. Applying integral and differential calculus with abstract symbols is, relatively speaking, straightforward. But replacing them with triangles and squares, well, that truly takes a master. Similarly, Einstein's theories are full of diagrams featuring trains, measuring rods, and clocks. Ultimately, Einstein developed two foundational theories. The first was the special theory of relativity, which describes the properties of light beams and space-time, and introduces the concept of symmetry based on rotation in 4 dimensions. The second was the general theory of relativity, which describes the nature of gravity as the curvature of space-time. But after these two monumental achievements, Einstein sought to accomplish a third, even more ambitious goal. He yearned to create a theory that would unify all the fundamental interactions of the universe into a single equation. He aimed to employ the language of field theory to create an equation combining Maxwell's theory of electricity and magnetism with his own theory of gravity. For several decades, he grappled with unifying these two theories, but ultimately he failed. In fact, it was Michael Faraday who first proposed unifying gravity with electromagnetism. He would often go to London Bridge and throw magnets off it, hoping to detect some measurable effect of gravity on a magnet. But he found nothing. One of the reasons Einstein was unsuccessful was that by the 1920s, a significant gap existed in our understanding of the world around us. It took an entirely new theory, quantum theory, for physicists to finally realize that at least one crucial piece was missing from the puzzle, the nuclear interaction. Yet, paradoxically, Einstein, despite being one of the founders of quantum theory, became its greatest adversary. He tirelessly leveled a torrent of criticism against quantum theory. Over the ensuing decades, this theory has withstood every conceivable experimental test, bringing into our lives a myriad of marvelous electronic devices that we now encounter everywhere, both at home and in the workplace. However, as we shall see, Einstein's profound and nuanced philosophical objections to quantum theory still resonate even today. The Battle of the Titans. Representing one side of this debate were Einstein and Schrödinger, who had, in their time, played a part in launching the quantum revolution. On the other side were Bohr and Werner Heisenberg, the architects of the new quantum theory. The culmination of this struggle was the historic Sixth Solvay Congress in 1930, held in Brussels. It was there that the era's pivotal debates unfolded, as these giants of physics confronted each other face to face in a battle over the very meaning of reality. Paul Ehrenfest later wrote about it, saying, "I will never forget watching the two opponents leave the university club. Einstein cut a majestic figure, walking calmly with a faint, ironic smile. Bohr, terribly upset, shuffled alongside him. In the hall, one could hear Bohr muttering a single word to himself, distractedly, 'Einstein, Einstein, Einstein.'" Einstein raised objection after objection against quantum theory, attempting to vividly demonstrate its inherent absurdity. But Bohr successfully parried Einstein's criticisms, one after another. When Einstein once again repeated that God does not play dice with the universe, Bohr is famously quoted as replying, "Stop telling God what to do." Princeton physicist John Wheeler said, "It was the greatest debate I have ever known in our intellectual history. For 30 years, I have never heard of a public argument between two greater men that lasted longer, nor one that was devoted to a deeper question, with deeper consequences for our understanding of this strange world of ours." Historians largely agree that Niels Bohr and the quantum rebels won this particular debate. Yet Albert Einstein managed to expose, and indeed demonstrate to everyone, the cracks in the very foundation of quantum mechanics. He effectively showed that this giant theory stood on philosophical feet of clay. The critical remarks he made back then can still be heard today, and at the heart of them, we find a rather interesting feline: Schrödinger's cat. Erwin Schrödinger devised a simple thought experiment that vividly illustrated the core of the problem. Imagine placing a cat inside a sealed box. Alongside it, you'd put a piece of uranium. When an elementary particle shoots out from the uranium, a Geiger counter is triggered, activating a gun that fires a bullet at the cat. The crucial question then becomes, is the cat alive or dead? Since the decay of a uranium atom is a purely quantum event, the cat itself must also be described from the perspective of quantum mechanics. Now, for Werner Heisenberg, as long as you haven't opened the box, the cat exists as a superposition of different quantum states. In other words, it's a sum of two waves. One wave describes a dead cat, while the other describes a living one. The cat is therefore neither alive nor dead, but rather a combination of these two states. The only way to tell if the cat is dead or alive is to open the box and make an observation. At that point, the wave function collapses into either a dead or a living cat. In other words, observation, which requires consciousness, determines existence. To Einstein, all of this was utter nonsense. It reminded him of Bishop George Berkeley's philosophy, who famously asked, "If a tree falls in a forest and there's no one around to hear it, does it make a sound?" Solipsists would, of course, say no. But quantum theory went even further, stating that if there's a tree in a forest with no one nearby, that tree exists as a superposition of many different states. For example, it could be a burnt tree, a young sapling, a log, or even a sheet of plywood. Only when you actually look at the tree does its wave function magically collapse into an ordinary tree. When guests visited Einstein at home, he would often ask, "Does the moon exist only because a mouse is looking at it?" Yet, no matter how absurd quantum theory seemed, no matter how much it contradicted common sense, it possessed one crucial merit. It was experimentally correct. The predictions of quantum theory have been verified to 11 decimal places, making it the most accurate theory of all time. Einstein, however, was prepared to concede that quantum theory was at least partially true. In 1929, he even nominated Schrödinger and Heisenberg for the Nobel Prize in Physics. Even today, there's no consensus among physicists regarding the cat problem. Niels Bohr's old Copenhagen interpretation, which posits that a true cat only emerges because observation causes its wave function to collapse, has largely fallen out of fashion. This is partly because with today's nanotechnology, we can actually manipulate individual atoms and conduct similar experiments. A more popular view has become the many worlds interpretation, where the universe effectively splits into two, with the cat being dead in one half and alive in the other. The success of quantum theory allowed physicists in the 1930s to turn their attention to a different challenge and set their sights on a new prize. They aimed to answer the age-old question, why does the sun shine? From time immemorial, many religions around the world deified the sun, placing it right at the heart of their mythologies. The sun was regarded as one of the most powerful gods ruling the heavens. For the Greeks, it was Helios, who majestically drove his gleaming chariot across the sky each day, illuminating our world and bestowing life. The Aztecs, Egyptians, and ancient Hindus each had their own versions of a sun god. However, during the Renaissance, some scientists attempted to investigate the sun through the lens of physics. They reasoned that if our star were made of wood or oil, all its fuel would have long since burned out. And if there's no air in the vast expanses of outer space, then the sun's flame would have been extinguished ages ago. So, the sun's perpetual energy remained a profound mystery. In 1835, a challenge was issued to scientists worldwide. The French philosopher Auguste Comte, founder of the philosophy of positivism, declared that while science was certainly a powerful tool, capable of unraveling many mysteries of the universe, one thing would forever remain beyond its grasp, he proclaimed. Even the greatest scientists will never succeed in answering the question of what the planets and the sun are made of. This was a reasonable challenge because the cornerstone of science is testability. All scientific discoveries, after all, must be reproducible and verifiable in a laboratory setting. However, it was quite obviously impossible to collect solar material in a bottle and bring it back to Earth. Consequently, the answer to this question seemed destined to remain a mystery to us forever. Ironically, just a few years after Comte made his pronouncement in his book Positive Philosophy, physicists were able to provide a fitting answer to his challenge. They discovered that the sun is primarily composed of hydrogen. It turned out Comte had made a small yet critically important error in his reasoning. Yes, science must always be testable. But as we've already established, a significant portion of scientific inquiry is conducted indirectly or through inference. In the early 19th century, Joseph von Fraunhofer developed the most precise spectrographs of his era. A spectrograph, for those unfamiliar, is essentially an instrument where light passes through a prism or another dispersive element. This then projects a spectrum, or a rainbow, onto a screen, revealing the different wavelengths of light present in the beam. When sunlight is passed through a spectrograph, narrow dark lines appear against the familiar rainbow spectrum. These lines emerge because electrons make quantum leaps from one orbit to another, either releasing or absorbing specific amounts of energy in the process. Crucially, since each chemical element produces its own unique characteristic lines, every spectral line is like a fingerprint. This allows an observer to determine the composition of the substance being examined. Beyond their scientific applications, spectrographs have also been instrumental in solving numerous crimes. They can help establish where a criminal came from, for instance by analyzing the mud on their boots. They can reveal the nature of a toxin and a poison, and even identify microscopic fibers and hairs. Essentially, spectrographs allow investigators to reconstruct a crime scene by determining the chemical composition of all substances present. It was, in fact, the analysis of these spectral lines in sunlight that enabled scientists to determine that the sun is composed predominantly of hydrogen. Furthermore, physicists discovered a new and previously unknown element on the sun itself. They named it helium, derived from the Greek word helios, meaning sun. So, quite remarkably, helium was first detected on the sun rather than on Earth. Soon after Fraunhofer's investigations, astronomers made another crucial discovery. By analyzing the light from distant stars, they found that these celestial bodies were also composed of elements common here on Earth. This was an incredibly significant finding because it indicated that the laws of physics are consistent not just within our own solar system, but throughout the entire universe. Once Einstein's theories gained widespread acceptance, physicists such as Arthur Eddington and Hans Bethe pieced all the data together. They then determined the fuel source powering the sun. The sun's immense gravitational field compresses hydrogen so intensely that protons begin to fuse, forming helium and subsequently heavier elements. Since the resulting helium nuclei weigh slightly less than the combined hydrogen nuclei from which they formed, this missing mass is transformed into energy, precisely as described by Einstein's famous formula. E equals mc squared. While physicists debated the startling paradoxes of quantum theory, storm clouds of war were gathering on the horizon. Adolf Hitler seized power in Germany in 1933, forcing many physicists to flee the country en masse, desperately seeking to escape arrest or a far worse fate. One day, while on the street, Erwin Schrödinger witnessed Nazis in their brown shirts harassing innocent Jewish people, ordinary passers-by and shopkeepers. When he attempted to intervene, they set upon him and began to beat him. The beating only ceased when one of the brown shirts recognized the scientist and told the others that the man they were assaulting was a Nobel laureate in physics. A deeply shaken Schrödinger soon left Austria. The finest minds in German science, alarmed by daily reports of repression, were leaving their homeland. Max Planck, the father of quantum theory and always a diplomat, personally pleaded with Hitler to halt the mass exodus of German scientists, warning that the country risked losing its brightest minds. But Hitler simply screamed at him, blaming everything on the Jews. Planck later wrote that it was impossible to reason with such a man. Tragically, Planck's own son was part of a group of conspirators who attempted to assassinate Hitler. For this, he was subjected to brutal torture and subsequently executed. For several decades, Albert Einstein was asked whether his equation could help unlock the truly immense amounts of energy trapped within the atom. Einstein consistently replied, "No, the energy released by a single atom is far too minuscule to be practically harnessed." Hitler, however, sought to leverage Germany's scientific prowess to create powerful, unprecedented weapons. instruments of terror like the V-1 and V-2 rockets, and the atomic bomb. After all, if the sun was powered by nuclear energy, then surely a superweapon could be forged from the same power source. The pivotal idea of how to practically harness Einstein's equation came from the physicist Leo Szilard. Even before Szilard, German physicists had demonstrated that a uranium nucleus, when bombarded by neutrons, could split apart, releasing additional neutrons in the process. Now, the energy released by splitting a single nucleus is exceedingly small, but Szilard realized that the nuclear power of uranium could be multiplied exponentially through a chain reaction. When one uranium nucleus splits, it releases 2 neutrons. These neutrons can then split 2 more uranium nuclei, which in turn will emit 4 neutrons. Then you get 8, 16, 32, 64, and so on neutrons. In other words, the number of split uranium nuclei would grow exponentially, releasing enough energy to flatten an entire city. Suddenly, the abstract discussions that had divided the physics community at the Solvay Congress became a matter of life and death, with the fate of nations, countries, and ultimately, all of human civilization at stake. Einstein was greatly alarmed when he learned that in Bohemia, the Nazis were shutting down and classifying uranium ore mines. Despite being a pacifist, Einstein felt compelled to write a momentous letter to United States President Franklin Roosevelt, urging the U.S. to develop an atomic bomb. Upon receiving the letter, Roosevelt gave the green light to the largest scientific undertaking in history, the Manhattan Project. Meanwhile, in Germany, the Nazis appointed Werner Heisenberg, widely considered the planet's foremost quantum physicist, to head their atomic project. According to some historians, the fear that Heisenberg might outpace the Allies in developing an atomic bomb was so profound that the Office of Strategic Services, the precursor to the CIA, devised a plan to assassinate him. In 1944, this mission was assigned to Mo Berger, a former professional baseball player and catcher for the Brooklyn Dodgers. Berg attended a lecture Heisenberg was giving in Zurich, carrying orders to kill the physicist if he, Berg, became convinced that the German atomic bomb project was nearing completion. This fascinating story is detailed in Nicholas Davidov's book, The Catcher Was a Spy. Fortunately, the Nazi atomic project lagged significantly behind the Allies. It was poorly funded and constantly fell behind schedule. Furthermore, its facilities were bombed by the Allies. More crucially, however, Heisenberg had not yet solved a fundamental problem essential for creating an atomic bomb. He hadn't determined the precise amount of enriched uranium or plutonium required to initiate a chain reaction, what we call critical mass. In fact, approximately 10 kilograms of uranium-235 were needed. To put that into perspective, it's an amount of uranium that could fit in the palm of your hand. After the war, the world began to grasp that the intricate and often bewildering equations of quantum theory held the key not only to atomic energy but, quite possibly, to the very fate of humanity. Physicists, however, gradually returned to a question that had stumped them before the war: how to create a complete quantum theory of matter, weak interactions, and ghostly particles. Meanwhile, research into the weak nuclear force, which is roughly 1 million times weaker than the strong nuclear force, was also making significant headway. For instance, the weak nuclear force isn't strong enough to hold together the components of many types of atomic nuclei. Consequently, these nuclei decay into smaller fragments and elementary particles. As we've already seen, radioactive decay is why the Earth's interior is so incredibly hot. And it's this weak nuclear force that is the source of energy for erupting volcanoes and powerful earthquakes. To explain this interaction, physicists introduced a new particle. A neutron, for example, is unstable and eventually decays into a proton and an electron. This process is known as beta decay. However, to make their calculations work, physicists had to introduce a third term into the equation, a particle called the neutrino. Neutrinos are sometimes referred to as ghost particles because they can pass through entire planets and stars without any interaction or absorption whatsoever. At this very moment, a stream of neutrinos from deep space is passing right through your body, with some of them having already traversed our planet. What's more, these particles could easily fly straight through a solid slab of lead, stretching all the way from Earth to the nearest star. Wolfgang Pauli, who predicted the existence of the neutrino in 1930, once famously complained, "I have done a terrible thing. I have introduced a particle that cannot be observed." But however elusive this particle was, it was eventually detected experimentally in 1956 by analyzing the powerful radiation emitted by a nuclear reactor. Even though neutrinos interact very little with ordinary matter, Physicists managed to compensate for this challenge by capitalizing on the fact that nuclear reactors emit a vast number of them. To truly understand the weak nuclear force, physicists once again introduced a new symmetry. Given that the electron and the neutrino form a pair of weakly interacting particles, it was hypothesized that they could be unified. This unification would then yield a new symmetry, which in turn could be combined with the older symmetry of Maxwell's theory. The resulting theory, dubbed the electroweak theory, successfully unified electromagnetism and the weak nuclear force. This electroweak theory, developed by Steven Weinberg, Sheldon Glashow, and Abdus Salam, earned them the Nobel Prize in 1979. So, rather than light unifying with gravity as Einstein had hoped, it actually chose to unify with the weak nuclear force. While the strong nuclear force is based on the Gell-Mann symmetry, which binds three quarks together to form protons and neutrons, the weak nuclear force relies on a less grand symmetry, the interchangeability of the electron and the neutrino, which then unifies with electromagnetism. However, despite the immense possibilities opened up by the quark model and the electroweak theory in describing the zoo of elementary particles, a glaring hole still remained in this description. The fundamental question was, what truly holds all these particles together? Given how successfully Maxwell's field had, in its time, predicted the properties observed in electromagnetism, physicists began exploring a new version of Maxwell's equations. This new version was proposed by Yang and Robert Mills in 1954. Instead of just the single field Maxwell had put forward in 1861, this theory introduced an entire family of such fields. And even the symmetry Gell-Mann had used in his theory to permute quarks was, in this new framework, employed to interchange the Yang-Mills fields. The idea was straightforward. If atoms are held together in a bound state by the electric field described by Maxwell's equations, then perhaps quarks are held together by what emerges from a generalization of Maxwell's equations, namely the Yang-Mills fields. Even the symmetry that describes quarks was now being applied to the Yang-Mills field. However, for several decades, this simple idea remained unutilized. This was because calculations of the properties of Yang-Mills particles consistently yielded infinite results, much like what happened in the early days of quantum electrodynamics. Unfortunately, the tricks that Feynman had once proposed for renormalization proved insufficient for the Yang-Mills theory. For many years, physicists desperately, but unsuccessfully, tried to find a finite theory for the nuclear force. Finally, an ingenious Dutch graduate student, Gerard Tooft, had the courage and persistence to tackle the problem head-on, to cut through the thicket of infinite terms and renormalize the Yang-Mills field. By that point, computers were powerful enough to analyze these infinities. When his computer program produced a series of zeros, representing the quantum corrections, he was finally convinced he was right. News of this breakthrough immediately captured the attention of physicists. Sheldon Glashow even exclaimed, "Either this guy is a complete idiot, or he is the greatest genius to have entered physics in years." It was this head-on solution to the problem that earned Hooft and his supervisor Martinus Veltman the Nobel Prize in 1999. Suddenly, a new field emerged, one that could link the known particles in the nuclear interaction and explain the weak nuclear force. This application of the Yang-Mills field to quarks was dubbed the gluon because it acted like a glue, binding quarks together. Computer simulations showed that the Yang-Mills field condenses into a sticky, taffy-like substance, which then, much like glue, binds the quarks together. For this to occur, quarks needed to come in three types, or colors, obeying Gell-Mann's three-quark symmetry. And so, a new theory of the strong nuclear force began to gain widespread popularity. It was christened quantum chromodynamics, or QCD, and today it stands as the most well-known description of the strong nuclear force. Next, we'll explore the Higgs boson, famously known as the God particle. Thus, a new theory gradually emerged from the chaos, eventually named the Standard Model of Particle Physics. The confusion surrounding the particle zoo slowly dissipated, replaced by a growing sense of order. The Yang-Mills field, known as the gluon, held quarks within neutrons and protons. Meanwhile, another Yang-Mills field, involving the W and Z particles, described the interaction between electrons and neutrinos. However, the final acceptance of the Standard Model was hindered by the absence of one crucial piece of the subatomic puzzle, what was called the Higgs boson, sometimes even referred to as the God particle. Simply having symmetry wasn't enough. A mechanism was needed to break this symmetry, because the universe we observe around us is not perfectly symmetrical. When we look at the universe today, it appears that all four fundamental interactions are independent of each other. Gravity, light, and the nuclear interactions seem, at first glance, to have nothing in common. But if we trace back further and further in time, these interactions begin to merge, perhaps converging into a single type of interaction at the moment the universe came into existence. A new picture began to emerge, one where particle physics was used to explain cosmology's greatest mystery, the birth of the universe. Suddenly, two very different fields of science, quantum mechanics and general relativity, began to converge into one. In this new framework, at the moment of the Big Bang, all four interactions were merged into a single superforce, or super interaction, which obeyed a grand symmetry capable of transforming all particles in the universe into one another. This super interaction was governed by what was called the God equation. It was precisely this symmetry that had eluded Einstein and other physicists. After the Big Bang, as the universe expanded and cooled, this grand super interaction, stemming from its underlying symmetry, began to break apart, leaving behind the fragmented symmetries of the weak and strong nuclear forces. In today's standard model, this process is known as symmetry breaking. Therefore, we need a mechanism that allows the initial symmetry to break in precisely the way required to produce the standard model, and it is at this very point that the Higgs boson enters the scene. To visualize this concept, imagine a dam. The water in the reservoir also possesses a certain symmetry. If you were to rotate all the water in a circular motion, its total mass would essentially remain unchanged and appear much the same as before. Now, we all know from experience that water always flows downhill. The reason for this, according to Newton, is that water constantly strives to reach a state of the lowest possible energy. If the dam were to break, the water would rush downwards to occupy a lower energy state. So, the water behind the dam is in a higher energy state. Physicists referred to the state of water behind a dam as a false vacuum, because it's unstable until the water settles into a true vacuum, that is, a state of minimal energy, down there at the bottom of the valley. Once the dam breaks, the initial symmetry is gone, but the water finds its true state of equilibrium. We can observe the same effect if we analyze boiling water. Just before boiling, the water is in a state of false vacuum. It's unstable, yet symmetrical, meaning you could rotate the entire body of water and its appearance wouldn't change. However, tiny bubbles gradually form, each existing in a lower energy state than the surrounding water. These bubbles then begin to expand until they merge sufficiently and the water boils. Following this scenario, the universe initially existed in a perfectly symmetrical state. At that time, all elementary particles were part of this very symmetry, and they all possessed zero mass. Due to their massless nature, they could be rearranged arbitrarily, and the equations would remain unchanged. However, for some unknown reason, such a universe was unstable. It was in a state of false vacuum. The field necessary for the transition to a true but broken vacuum is known as the Higgs field. Much like Faraday's electric field, which permeates all of space, the Higgs field also filled all of space-time. But for some reason, the symmetry of the Higgs field began to break. Tiny bubbles started to form within the Higgs field. Outside these bubbles, all particles remain massless and symmetrical, whereas inside a bubble, some particles acquired mass. As the Big Bang unfolded, the bubble rapidly expanded. The particles within it began to acquire different masses, and the initial symmetry was broken. Eventually, it turned out that the entire universe existed in a new vacuum state, contained within one giant bubble. And so, by the 1970s, the painstaking work of dozens of physicists began to pay off. After decades of groping in the dark, they finally saw the pieces of the puzzle falling into place. They realized that by bringing together three theories, representing the strong, weak, and electromagnetic interactions, they could create a system of equations that would truly match the results observed in the laboratory. The key was to create patterns of symmetry by combining three separate, smaller-scale symmetries. Firstly, this symmetry described the strong nuclear interaction, allowing three quarks to be arbitrarily swapped. Secondly, it described the weak nuclear interaction, permitting the swapping of electrons and neutrinos. And thirdly, this symmetry described Maxwell's original field. The resulting theory seemed rather clunky, but its success was hard to argue with. What's remarkable is that the standard model could accurately predict the properties of matter in the past, right down to a fraction of a second after the Big Bang. The standard model itself is a curious collection of elementary particles that accurately describe our quantum universe. It includes 36 quarks and antiquarks, 12 weakly interacting particles and antiparticles known as leptons, and a large number of Yang-Mills fields and Higgs bosons, particles that arise from the excitation of the Higgs field. However, despite the standard model being the most comprehensive representation of our understanding of the subatomic world, it still contained numerous gaps. Firstly, it made no mention of gravity. This was a huge problem, as gravity is precisely the force that determines the large-scale behavior of the universe. Yet, whenever physicists tried to incorporate gravity into the Standard Model, they found themselves unable to solve the associated equations. Quantum corrections, instead of being small, turned out to be infinite, exactly as was the case with quantum electrodynamics and Yang-Mills particles. Consequently, the Standard Model was unable to shed light on some of the universe's deepest secrets. For example, what happened before the Big Bang, or what lies inside a black hole. Secondly, the Standard Model was constructed by artificially stitching together theories describing different interactions, so the resulting theory resembled a patchwork quilt. One physicist famously compared it to taping together a platypus, an anteater, and a whale, then declaring the result the most elegant creation of nature. In reality, he suggested, only its mother could truly love such a creature. Thirdly, the Standard Model had a multitude of undetermined parameters, such as the masses of quarks and the strengths of interactions. Moreover, it contained around 20 constants that had to be manually inputted without any understanding of their origin or true nature. Fourthly, the Standard Model featured not one, but 3 identical copies or generations of quarks and gluons, electrons, and neutrinos. So, in total, there are 36 quarks with 3 colors and 3 generations, along with their corresponding antiparticles and 20 free parameters. Physicists found it difficult to accept something so cumbersome and unwieldy as the fundamental theory of the universe. The stakes are incredibly high, which is why many nations are prepared to invest billions in developing the next generation of particle accelerators. To date, the Large Hadron Collider, located near Geneva in Switzerland, has dominated the headlines. It's the largest scientific instrument ever constructed, costing more than $12 billion and measuring approximately 27 kilometers in circumference. The LHC resembles a gigantic torus, straddling the border between Switzerland and France. Inside its tubes, protons are accelerated to extremely high energies. Then, they collide with another high-energy beam of protons, traveling in the opposite direction. These collisions release 14 trillion electron volts of energy, creating an intense shower of elementary particles. Scientists then attempt to analyze these particles using the world's most powerful computers. The LHC's primary objective is to recreate the conditions that existed during the universe's earliest moments, right after the Big Bang, and in doing so, to generate these unstable particles. Then, in 2012, the Higgs boson was finally discovered, proving to be the last missing piece of the Standard Model. This marked a momentous day for high-energy physics, but scientists knew there was still a long road ahead. The Standard Model effectively describes all particle interactions, from the deepest parts of a proton to the most distant reaches of the visible universe. However, its main drawback is its inherent clumsiness. Historically, whenever physicists probed the fundamental nature of matter, new and elegant symmetries consistently emerged. It became difficult to believe that, at its most fundamental level, nature would favor such an inelegant theory. Despite the undeniable practical successes of the Standard Model, it's clear to everyone that it's merely a prelude, a warm-up act, for a more definitive theory yet to be discovered. Meanwhile, emboldened by the striking successes of quantum theory in its application to elementary particles, physicists began to revisit the general theory of relativity, which had largely languished in obscurity for several decades. Now, physicists set their sights on an even more ambitious goal: to unify the Standard Model with gravity. The only missing piece was to create a quantum theory of gravity itself. This would in essence be a true theory of everything, where all quantum corrections for both the Standard Model and General Relativity would be fully computable. Previously, renormalization theory had served as a clever trick, allowing physicists to effectively cancel out all quantum corrections within the Standard Model. The key lay in representing electromagnetic and nuclear forces as particles, specifically photons and Yang-Mills particles. Then, with a metaphorical wave of a magic wand, all divergencies would seemingly vanish, being compensated for elsewhere. All those troublesome infinities were, in effect, swept under the rug. Physicists, perhaps a bit naively, followed a time-honored tradition. They took Einstein's theory of gravity and introduced a new point particle of gravity, which they dubbed the graviton. So, the smooth surface that Einstein had introduced, intended to represent the fabric of space-time in his theory, suddenly found itself surrounded by a cloud of trillions of tiny particles, gravitons. Alas, the carefully assembled collection of tricks that physicists had diligently developed over the preceding 70 years to eliminate inconvenient divergencies simply didn't work when applied to the graviton. The quantum corrections generated by gravitons proved to be infinite, refusing to be absorbed or compensated for elsewhere. At this point, physicists found themselves at a dead end. Their run of luck had simply expired. Following this disappointment, frustrated physicists shifted their focus to a more modest objective. Unable to formulate a complete quantum theory of gravity, they instead attempted to calculate what happens to ordinary matter during quantization, leaving gravity itself untouched. This involved calculating quantum corrections stemming from stars and galaxies, without directly incorporating gravitational effects. By focusing solely on the quantization of the atom, scientists hoped to gain a deeper insight into their broader goal: the formulation of a quantum theory of gravity. While a more modest undertaking, this task nevertheless opened the floodgates to an astonishing array of fascinating new physical phenomena, each challenging our fundamental understanding of the universe. Suddenly, quantum physicists found themselves confronting the most bizarre phenomena in the cosmos: black holes, wormholes, dark matter, and dark energy, the possibility of time travel, and even the very birth of the universe itself. However, the discovery of these peculiar cosmic phenomena also presented a significant challenge to the theory of everything. It now had to account for not only the familiar elementary particles of the Standard Model, but also all these strange new occurrences that had truly pushed the boundaries of human imagination. So, as we look back, we can see that at the turn of the 19th and 20th centuries, physics was largely built upon two great pillars: Newton's law of universal gravitation and Maxwell's equations for light. Einstein recognized that these two theories were in conflict, and he understood that one of them was destined to fall. The eventual downfall of Newtonian mechanics then spurred the great scientific revolutions of the 20th century. It's quite possible that history is repeating itself even today. Once again, physics finds itself resting on two distinct pillars. On one hand, there's the theory of the very large, Einstein's theory of gravity, which explains black holes, the Big Bang, and our expanding universe. On the other hand, we have the theory of the very small, quantum theory, which accounts for the behavior of elementary particles. The fundamental issue, however, is that these two theories fundamentally contradict each other. They are built upon entirely different principles, distinct mathematical frameworks, and even contrasting philosophies. Our hope is that the next great scientific revolution will ultimately unify these two monumental pillars. It all began in 1968. When two young physicists, Gabriele Veneziano and Mohiko Suzuki, while delving into mathematical texts, stumbled upon a peculiar formula. This formula had been derived by the mathematician Leonhard Euler all the way back in the 18th century. What was so surprising was that this odd formula seemed to describe the scattering of two elementary particles. How could an abstract formula from the 18th century possibly describe results obtained from modern particle accelerators? To physicists, that simply made no sense. Later on, physicists, including Yoichiro Nambu, Holger Nielsen, and Leonard Susskind, realized that this formula actually represented the interactions of two strange, incredibly fast strings. They were then able to extend it to a whole host of equations representing the scattering of multiple strings. Next, researchers managed to incorporate rotating particles into string theory. String theory, it seemed, had become something of an oil well, unexpectedly gushing forth a fountain of new equations. Now, the author recalls, personally this was unsatisfactory to me, because ever since Faraday's time, physics had been represented by fields that contained a vast amount of information in a compact form. String theory, in contrast, was simply a collection of disparate equations. However, by developing what's known as string field theory, and using our equations, it became possible to condense string theory into a single field theory equation, no longer than an inch. From this torrent of equations, a new picture began to emerge. Why are there so many particles? Much like Pythagoras over 2,000 years ago, the theory suggested that each musical note, each vibration of a string, describes a particular particle. So, electrons, quarks, and Yang-Mills particles are nothing more than different notes played on one and the same vibrating string. What's particularly fascinating about this theory is that it necessarily incorporates gravity. The graviton, for example, appears within it as one of the lowest string vibrations, without any additional assumptions. What's more, even if Einstein had never existed, his theory of gravity could have been discovered simply by looking at the lowest vibration of that very same string. As physicist Edward Witten once remarked, string theory is extraordinarily compelling because it essentially forces gravity upon us. All known consistent string theories incorporate gravity. So, if gravity is impossible in quantum field theory as we know it, then in string theory it is absolutely essential. However, as the theory continued to develop, more and more fantastic and utterly unexpected features began to emerge. For example, it was discovered that it could only exist in 10 dimensions. This sent physicists into a state of genuine shock, as nothing like it had ever been seen before. You see, a conventional theory can be expressed in any number of dimensions you like. We simply discard all other possibilities because, quite obviously, we live in a three-dimensional world. We can only move forwards and backwards, left and right, and up and down. If you add time, then 4 dimensions are perfectly sufficient to pinpoint the location of any event in the universe. For instance, if we want to meet someone in Manhattan, it's enough to say, let's meet at the corner of 5th Avenue and 42nd Street on the 10th floor at noon. Moving in dimensions beyond these 4 is simply impossible for us, no matter how hard we try. What's more, our brains aren't even capable of visually imagining what it would be like to move in higher dimensions. That's why research into multidimensional string theory is conducted purely mathematically. However, in string theory, the dimension of spacetime is fixed at 10 dimensions. In any other dimension, the theory mathematically collapses. The author recalled, "I still remember the shock physicists experienced when string theory suddenly posited that we live in a 10-dimensional universe. Most physicists saw this as definitive proof that the theory was fundamentally flawed. In fact, when John Schwartz, one of the leading architects of string theory, would encounter Richard Feynman in the Caltech elevator, Feynman would often tease him, asking, 'Well, John, how many dimensions are you in today?' Nevertheless, over the years, physicists began to demonstrate that all competing theories suffered from fatal flaws. For example, many could be ruled out simply because their quantum corrections turned out to be infinite or anomalous. In other words, mathematically inconsistent. So, gradually, physicists began to warm to the idea that our universe might, after all, be 10-dimensional. Finally, in 1984, John Schwartz and Michael Green demonstrated that string theory was free from all the problems that had doomed other contenders for a unified field theory. If string theory is correct, then the universe might have originally been 10-dimensional. However, such a universe proved unstable and 6 of the 10 dimensions somehow curled up, becoming too small to be observed. This implies that our universe might actually be 10-dimensional, but atoms are simply too large to penetrate these tiny higher dimensions. Despite all the apparent craziness of string theory, one particular ability keeps it firmly in the spotlight. It successfully marries 2 great physical theories, namely general relativity and quantum theory, and thus offers us the ultimate theory of quantum gravity. And this is precisely why there's so much excitement surrounding string theory. As previously mentioned, when you add quantum corrections or a Yang-Mills particle, you typically get a cascade of divergences that need to be eliminated. However, all these efforts lead nowhere if we try to force a marriage between 2 great theories of nature, relativity theory and quantum theory. To apply the quantum principle to gravity, we typically break it down into packets of energy, or quanta, known as gravitons. Then, we calculate the collisions of gravitons with each other and with matter particles such as electrons. But even then, the entire set of tricks devised by Feynman and Hooft yields no results. The quantum corrections, caused by the interaction of gravitons with other gravitons, diverge and are completely intractable using the methods discovered by previous generations of physicists. Here then is the next piece of magic. String theory has the remarkable ability to eliminate those problematic divergences that have plagued physicists for nearly a century. And once again, this magic is achieved through symmetry. Historically, the symmetry of an equation was considered a positive quality, but it was often viewed as a luxury, not a strict necessity. However, in quantum theory, symmetry becomes the single most crucial property in physics. When you calculate the collision of 2 gravitons, for instance, the answer turns out to be infinite, and therefore meaningless. But when 2 strings collide, we get 2 distinct terms, one from bosons and one from fermions. In string theory, these 2 terms precisely cancel each other out, helping to create a finite theory of quantum gravity. As we've established, when calculating quantum corrections to a particular theory, they often turn out to be divergent, meaning infinite, or anomalous, which means they violate the theory's original symmetry. It's only in recent decades that physicists have truly understood that symmetry is not just a pleasant attribute of a theory, but rather its central component. The requirement that a theory be symmetric is often powerful enough to expel the divergences and anomalies inherent in non-symmetric theories. Symmetry, then, is the sword with which physicists conquer the dragons unleashed by quantum corrections. As previously mentioned, Paul Dirac discovered that his equations for the electron predicted that the electron possessed spin, a mathematical property of the equation that resembles the ordinary rotation we observe in everyday life. Later, physicists found that all elementary particles have spin, but spin comes in 2 distinct types, When measured in specific quantum units, spin can either be an integer, such as 0, 1, or 2, or a half integer, like 1/2 or 3/2. Particles with integer spin describe the fundamental interactions in the universe. These include the photon and the Yang-Mills particle, both with spin 1, as well as the graviton, the particle of gravity, with spin 2. They are known as bosons, named after the Indian physicist Satyendra Nath Bose. So, we can say that the natural interactions are mediated by bosons. Then there are the particles that constitute the matter of the universe. These possess half-integer spin. Examples include electrons, neutrinos, and quarks, all with a spin of 1/2. These particles are called fermions, after Enrico Fermi. From them we can construct the other constituent particles of an atom, namely protons and neutrons. So, the atoms that make up our bodies are essentially collections of fermions. In essence, there are two main types of subatomic particles: fermions, which constitute matter, and bosons, which mediate the fundamental forces. Fermions include electrons, quarks, neutrinos, and protons, while bosons comprise photons, gravitons, and Yang-Mills particles. Subsequently, Gershom Goldhaber, Akihiro Karita, and Jean-Luc Gervais demonstrated that string theory possesses a new type of symmetry, which they called supersymmetry. Since then, the concept of supersymmetry has been profoundly expanded, becoming the most comprehensive symmetry ever discovered in physics. As we've emphasized, for physicists, you see, beauty often lies in symmetry, as it allows us to find connections between different particles. Supersymmetry, remarkably, has the potential to unify all particles in the universe. As mentioned earlier, symmetry allows us to swap components of an object while keeping the original object unchanged. Here, in the context of the equations, particles effectively swap places. Fermions step into the roles of bosons and vice versa. This remarkable ability for all particles in the universe to freely exchange roles and transform into one another becomes a central, defining characteristic of string theory. This implies that every particle has a superpartner, often referred to as an S-particle or superparticle. For instance, the superpartner of an electron is called a selectron, a quark superpartner is a squark, and a lepton superpartner, like that of an electron or neutrino, is called a slepton. But something truly remarkable happens in string theory. When calculating quantum corrections, we find two components, one arising from fermions and another from bosons. Miraculously, these two components turn out to be identical in magnitude, but precisely opposite in sign. One term might be positive, while at the same time there is another term that is negative. When added together, they perfectly cancel each other out, always leaving a finite result. For nearly a century, physicists struggled to unite the theory of relativity with quantum theory. However, the symmetry between fermions and bosons, known as supersymmetry, allows many infinities to mutually cancel each other out. Indeed, physicists soon discovered other mechanisms for eliminating infinities, always resulting in a finite outcome. And this, fundamentally, is the root of the excitement surrounding string theory, its unique ability to unify gravity and quantum theory. No other theory can make the same claim. This potentially addresses Paul Dirac's initial objection. He deeply disliked renormalization theory because, despite its fantastic and undeniable successes, it essentially proposed adding and subtracting quantities that were, in fact, infinite in size. Here, however, we see that string theory is inherently finite, requiring no renormalization whatsoever. This, incidentally, aligns perfectly with the vision Einstein himself proposed. He once compared his theory of gravity to marble, smooth, elegant, and perfectly polished. Matter, on the other hand, he likened to wood. A tree trunk, you see, is gnarled, chaotic, rough, and lacks any precise geometric structure. His ultimate goal was to create a unified theory that would connect both marble and wood, essentially a theory made entirely of marble. This was Einstein's dream. String theory, it seems, might just complete this picture. Supersymmetry has the remarkable ability to transform marble into wood and vice versa. In this context, marble and wood are simply two sides of the same coin. In this particular analogy, marble represents bosons, while wood represents fermions. While we currently lack experimental evidence for the existence of supersymmetry in nature, it's such an elegant and beautiful concept that it has truly captivated the imagination of the physics community. As Steven Weinberg once put it, although symmetries are hidden from us, we can sense that they are implicitly present in nature, governing everything around us. This is the most exciting idea I know. nature is much simpler than it appears. Nothing gives me more hope than the idea that our generation genuinely holds the key to the universe, that within our lifetimes, we might be able to explain why everything visible in this vast universe, with its galaxies and particles, is logically inevitable. So, to summarize what we've discussed, it's clear now that symmetry may well be the key to unifying all the laws of the universe. Symmetry, you see, creates order out of chaos. From the chaos of chemical elements and elementary particles, both Mendeleev's periodic table and the Standard Model are able to establish order by arranging them neatly and symmetrically. What's more, symmetry helps fill in the gaps. It allows us to pinpoint deficiencies in theories and, in doing so, predict the existence of new types of elements and elementary particles. Symmetry unites seemingly unrelated and utterly unexpected objects. It finds connections between space and time, matter and energy, electricity and magnetism, as well as fermions and bosons. Finally, symmetry uncovers unexpected phenomena. It has, for instance, predicted the existence of new phenomena such as antimatter, spin, and quarks. Symmetry also eliminates undesirable consequences that could potentially undermine a theory. Quantum corrections, for example, often exhibit catastrophic divergences and anomalies, all of which can be resolved through the application of symmetry. Furthermore, symmetry profoundly alters the initial classical theory. The quantum corrections to string theory are so rigorous, in fact, that they fundamentally change the original theory, fixing the dimensionality of space-time itself. It's believed that at the very beginning of time, there existed a single, unified super-interaction whose symmetry encompassed all the particles of the universe. However, this situation was unstable, and the symmetry began to break down. First, gravity separated, followed by the strong and weak nuclear forces, leaving only the electromagnetic interaction. This is why the universe today appears fragmented, with all interactions seeming vastly different from one another. The task for physicists, then, is to reassemble these pieces into a single, unified interaction. Superstring theory possesses all the necessary properties, and its symmetry is precisely supersymmetry, the symmetry of bosons and fermions. Supersymmetry, in turn, is the most comprehensive symmetry ever discovered in physics, capable of uniting all known particles in the universe. We still need to take a crucial final step in developing string theory, uncovering its fundamental physical principles. The thing is, we still don't fully understand how to derive the entire theory from a single foundational equation. Then, in 1995, string theory underwent another significant metamorphosis, giving birth to what's known as M-theory. The problem with the initial string theories was that there were 5 distinct versions of quantum gravity, each finite and well-defined. All 5 of these seemingly disparate theories looked quite similar, with the only real difference being how the spins were organized. This immediately raised a question. Why 5? After all, most physicists believe the universe should be unique. Physicist Edward Witten then discovered that there was actually a hidden 11-dimensional theory which he named M-theory. This theory was based on membranes, structures like the surfaces of spheres and tori, rather than just simple strings. He explained the existence of the 5 distinct theories by demonstrating that an 11-dimensional membrane could be compactified into a 10-dimensional string in 5 different ways. In other words, all 5 versions of string theory were simply different mathematical representations of the very same M-theory. So, in essence, string theory and M-theory are one and the same, with string theory being the reduction of the 11-dimensional M-theory down to 10 dimensions. But how, you might ask, can a single 11-dimensional theory give rise to 5 10-dimensional theories? Imagine, if you will, an inflatable beach ball. If you let the air out, the ball will deflate, starting to resemble a sausage. If you then remove the remaining air, that sausage will transform into a string. Therefore, a string is actually just a deflated membrane in disguise. If we start with an 11-dimensional beach ball, it can be mathematically shown that there are 5 distinct ways to deflate it, turning it into a 10-dimensional string. Or, consider the ancient parable of the blind men encountering an elephant for the very first time. One of them, upon touching the animal's ear, declared that the elephant was flat and 2-dimensional, like a fan. Another, feeling its tail, concluded that the elephant was like a rope or a 1-dimensional string. A third, examining its leg, determined that the elephant was a 3-dimensional drum or cylinder. But in reality, if you step back and ascend into the 3rd dimension, you can see the elephant as the 3-dimensional animal it truly is. Similarly, the 5 different string theories are like the ear, the tail, and the leg, but we as yet have to see the entirety of M-theory. As we've discussed, string theory continued to open up new horizons over time, Shortly after M-theory was proposed in 1995, Juan Maldacena made another astonishing discovery in 1997. He shocked the physics community by demonstrating something once thought impossible. Specifically, he showed that the supersymmetric Yang-Mills theory, which describes the behavior of elementary particles in 4 dimensions, is dual, that is, mathematically equivalent, to a particular string theory in 10 dimensions. This generated tremendous excitement within the physics community. By 2015, 10,000 articles had been published referencing Maldacena's work, making it the most influential paper in high-energy physics. Symmetry and duality are related, yet distinct, concepts. Symmetry occurs when we rearrange components within a single equation, and the equation itself remains unchanged. Duality, on the other hand, arises when we demonstrate that 2 entirely different theories are, in fact, mathematically equivalent. It's remarkable that string theory possesses both of these highly non-trivial qualities. As we've seen, Maxwell's equations exhibit a duality between electric and magnetic fields. The equations remain unchanged if we swap these 2 fields, essentially transforming electric fields into magnetic ones and vice versa. We can observe this mathematically because electromagnetic equations often contain terms like E squared plus B squared. These terms remain invariant when we rotate the 2 fields, effectively transforming them into each other, much like in the Pythagorean theorem. Similarly, there are 5 distinct theories in 10 dimensions that can be proven to be dual to one another, because they all actually represent a single 11-dimensional M-theory. Ultimately, duality reveals that 2 seemingly different theories are actually just 2 aspects of the very same underlying theory. Maldacena, however, demonstrated yet another type of duality, one between strings in 10 dimensions and Yang-Mills theory in 4 dimensions. This development was entirely unexpected, but it carried significant implications. It meant that deep, unforeseen connections exist between gravitational and nuclear interactions, even though they are defined in completely different dimensions. Typically, dualities are found between strings of the same dimensionality, representing terms that describe those strings. For instance, we can often substitute one string theory for another. This creates an intricate web of dualities among various string theories that are defined in the same dimension. However, a duality between 2 objects defined in different dimensions was truly unprecedented. This is far from being merely an academic question, as it has far-reaching consequences for our understanding of the nuclear interaction. For example, we previously learned that the best description of the nuclear interaction is provided by a gauge theory in 4 dimensions, represented by the Yang-Mills field. Yet no one has ever managed to find a single exact solution for the Yang-Mills field. However, since a gauge theory in 4 dimensions can be dual to a string theory in 10 dimensions, this suggests that the key to understanding the nuclear interaction might lie within the theory of quantum gravity. This was a revelation, as it implied that the fundamental properties of the nuclear interaction, such as the mass of a proton, for instance, might be best described by string theory. This, in turn, sparked a peculiar identity crisis among physicists. Those who work exclusively in nuclear interaction research dedicate all their time to studying 3-dimensional objects like protons and neutrons. They often scoff at physicists who delve into theoretical reasoning in higher dimensions. But with this new duality between gravity theory and gauge theory, they suddenly found themselves trying to learn everything they could about 10-dimensional string theory. This is because it might hold the key to understanding the nuclear interaction in 4 dimensions. This strange duality led to yet another unexpected discovery, known as the holographic principle. A hologram, essentially, is a 2-dimensional sheet of plastic that contains an image of 3-dimensional objects, encoded in a special way. When a laser beam is directed onto this flat screen, a 3-dimensional image appears. In other words, all the information needed to create a 3-dimensional image is encoded and imprinted onto that flat 2-dimensional screen, using lasers. This is similar to how R2-D2 from Star Wars projected the image of Princess Leia. It's also the technique used to create the haunted mansions at Disneyland, where 3-dimensional ghosts appear to glide around you. This principle also holds true for black holes. As we saw earlier, if you throw an encyclopedia into a black hole, quantum mechanics dictates that the information contained within the book cannot simply vanish. So, where does it go? One theory postulates that this information is distributed across the surface of the black hole's event horizon. This means the black hole's 2-dimensional surface contains complete information about all the 3-dimensional objects that have fallen inside. From this, similarly, far-reaching conclusions emerge for our very concept of reality. We are convinced that we are 3-dimensional objects, capable of moving through space, and describable by 3 numbers: length, width, and height. But this, perhaps, is an illusion. Perhaps we all live in a hologram. Maybe the three-dimensional world we perceive is merely a shadow of a real world that is actually 10 or 11-dimensional. When we move in three spatial dimensions, we are in essence perceiving the movements of our true selves in 10 or 11 dimensions. Think of it this way. When we walk down the street, our shadow follows us, moving similarly to us, except that it exists in 2 dimensions. Similarly, we ourselves might be shadows moving in 3 dimensions, while our true selves are simultaneously moving in 10 or 11 dimensions. Ultimately, we see that over time, string theory yields new and completely unexpected results. This suggests that we still don't truly grasp the fundamental principles underlying it. It's entirely possible that we shouldn't even be talking about strings at all, because when the theory is formulated in 11 dimensions, these strings can actually be described as membranes. This is precisely why it's too early to test string theory experimentally. Once we manage to uncover the true principles behind it, we might just find a way to test it. Only then will we be able to say definitively, and once and for all, what string theory truly is. A theory of everything, or a theory of nothing. Despite its theoretical successes, string theory still has its share of weaknesses. Any theory with such grand claims, like string theory, naturally attracts the attention of a whole army of critics. We constantly have to remind ourselves of Carl Sagan's words, that extraordinary claims require extraordinary evidence. I'm also reminded of Wolfgang Pauli, who had a masterful way of putting people in their place. Listening to someone's presentation, he might simply say, "What you said was so confused that one could not tell whether it was nonsense or not." He also famously said, "I don't mind you thinking slowly, but I object to you publishing faster than you think." If he were alive today, he might very well address those same words to string theory. The debate is so heated that the best minds in physics are actually split right down the middle on this issue. Science hasn't seen such a division since the Sixth Solvay Conference in 1930, where Einstein and Bohr famously clashed over quantum theory. Even Nobel laureates have taken opposing stances. Sheldon Glashow wrote, "Over the years, after intense work by dozens of the best and brightest, not a single verifiable prediction has been obtained, nor are any likely to be expected in the near future." Gerard T. Hooft went even further, stating that the interest surrounding string theory could be compared to American television series, all hype and no substance. Others, however, extol the virtues of string theory. David Gross wrote, "Einstein would have been pleased at least with the goal, if not the realization. He would have liked the fact that at its heart lies a geometric principle which, alas, we do not yet truly understand." Steven Weinberg compared the history of string theory's development to the quest for the North Pole. On ancient maps of the Earth where the North Pole was supposed to be, a vast, bottomless hole was depicted, but no one had ever actually seen it. From any point on Earth, compasses pointed to this mythical location, yet all attempts to find the infamous North Pole ended in failure. Deep down, ancient mariners knew that some North Pole must exist, but no one could prove it. Some even doubted its very existence. However, in 1909, after centuries of speculation and conjecture, Robert Peary finally reached the true North Pole. String theory critic Glashow himself acknowledged that he was in the minority in this debate. He once remarked, "I feel like a dinosaur in a world of upstart mammals." Several main objections are raised against string theory. Its critics argue that, firstly, the theory is all hype. Secondly, that beauty in itself is an unreliable guide in physics. Thirdly, that it predicts too many universes. And most importantly, that it is untestable. The great astronomer Kepler was once seduced by the power of beauty. He fell in love with a theory proposing that the solar system resembled a collection of regular polyhedra nested one within another. Centuries ago, the Greeks identified 5 such polyhedra, namely the cube, the pyramid, and so on. Kepler observed that by sequentially nesting these polyhedra inside one another, much like Russian nesting dolls, one could reproduce certain details of the solar system. The idea was beautiful, but it turned out to be completely wrong. More recently, a number of physicists have criticized string theory on the grounds that beauty is a deceptive criterion in physics. Just because string theory possesses brilliant mathematical properties does not in itself mean that it contains even a shred of truth. They rightly pointed out that beautiful theories can sometimes lead to dead ends. However, poets often quote John Keats's poem, Ode on a Grecian Urn, "Beauty is truth, truth beauty. That is all ye know on earth, and all ye need to know." Paul Dirac certainly followed this principle when he wrote, "A scientific man, in his efforts to express the fundamental laws of nature in mathematical form, should strive mainly for mathematical beauty." Moreover, according to him, he discovered his famous theory of the electron not by poring over data, but by playing with mathematical formulas. But however powerful a factor beauty may be in physics, it can certainly lead us astray. As physicist Sabine Hossenfelder wrote, beautiful theories have been disproven by the hundreds. Theories about unified interactions, about new particles, about extra symmetries in other universes. All these theories were wrong. Clearly, relying solely on beauty is not the best strategy. Critics contend that while string theory is mathematically beautiful, this may have absolutely no bearing on physical reality. There's certainly some truth to such a remark, but it's important to understand that certain aspects of string theory, such as supersymmetry, cannot be dismissed as useless for physics. While evidence for the existence of supersymmetry has yet to be found, it has been shown to be essential for resolving many defects within quantum theory. By mutually compensating bosons and fermions, supersymmetry allows us to solve a long-standing problem, eliminating the divergencies that plague quantum gravity theory. Not every beautiful theory is applicable in physics, but without exception, all existing fundamental physical theories possess some inherent beauty or symmetry. So the obvious question arises, can we actually test this theory? One of the primary criticisms often leveled against string theory is precisely its apparent untestability. The energy associated with gravitons, for instance, is known as Planck energy. This energy is a staggering quadrillion times greater than anything we can currently generate at the Large Hadron Collider. Just imagine trying to construct a Large Hadron Collider that's a quadrillion times bigger than the one we have now. To directly test the theory, we would probably need a particle accelerator the size of an entire galaxy. Furthermore, each solution within string theory actually represents an entire universe, and it appears there's an infinite number of these solutions. So, to directly verify our theory, we'd essentially need to create brand new universes in a laboratory setting. In other words, it seems only a divine entity could directly test this theory, as its fundamental principles involve entire universes, not just simple atoms or molecules. So, initially, it might seem that string theory lacks a crucial quality for any scientific theory: testability. However, its proponents remain undeterred by this challenge. As we've discussed, science more often than not relies on indirect methods. It operates by studying echoes from phenomena like the Sun or the Big Bang and similar events. We, for example, are searching for echoes of 10 and 11 dimensions. Perhaps hidden evidence for string theory is all around us, but we should be listening for its echoes rather than attempting to observe it directly. One potential signal emanating from hyperspace is, in fact, the existence of dark matter. Until relatively recently, it was widely believed that our universe was composed primarily of atoms. However, astronomers were astonished to discover that atoms like hydrogen and helium account for only 4.9% of the universe's total mass. In reality, the overwhelming majority of the universe is hidden from our view, existing instead as dark matter and dark energy. It's important to remember that dark matter and dark energy are not the same phenomenon. Within the universe, 26.8% of its mass is attributed to dark matter, an invisible substance that envelops galaxies, preventing them from flying apart. Meanwhile, 68.3% of the universe is made up of dark energy, which is even more mysterious. This is the energy of empty space, which pushes galaxies apart and causes them to accelerate away from one another. Perhaps, then, the proof for a theory of everything is hidden precisely within this invisible universe. Dark matter is both strange and, well, invisible. It's actually responsible for holding the Milky Way galaxy together, preventing its constituent stars from flying off in all directions. Since dark matter has mass but no charge, if you tried to pick it up, it would pass right through your fingers as if they weren't there. It would then fall downwards, straight through the floor, through the Earth itself, and emerge on the other side. There, gravity would gradually cause it to change direction and return to your location. And so, it would continue to oscillate between you and the other side of the Earth, essentially oblivious to the planet itself. However strange dark matter may seem, we actually know it must exist. If you analyze the rotation of the Milky Way galaxy and apply Newton's laws, you'll find there isn't nearly enough visible mass to counteract the centrifugal force. Given the observed masses, galaxies throughout the universe should be unstable and theoretically ought to be flying apart. Yet they've remained intact for billions of years. So this leaves us with two possibilities. First, Newton's equations might be incorrect when applied to galaxies. Or second, there's an invisible entity that allows galaxies to maintain their integrity. As a historical parallel, remember that the planet Neptune was discovered in precisely this manner. Its existence was postulated to explain the observed deviations in Uranus's orbit from theoretical predictions. Currently, one of the leading candidates for dark matter is what we call weakly interacting massive particles, or WIMPs. A likely example of such a particle is the photino, which is a supersymmetric partner of the photon. Photons are stable, possess mass, are invisible, and have no charge, which perfectly aligns with the characteristics of dark matter. Physicists believe that Earth is constantly moving through an invisible stream of dark matter, a stream that is probably passing through your body right this very moment. When a photon collides with a proton, it can cause that proton to decay into a shower of elementary particles, which we could then potentially detect. Today, there's already a massive detector, about the size of a swimming pool, containing a vast quantity of liquid, specifically xenon and argon. This detector might one day capture a flash of light, generated by a collision involving a photon. Around 20 groups are actively engaged in the search for dark matter. They often work deep underground in mines, far away from interfering cosmic ray collisions. It's certainly possible that our instruments will eventually register collisions involving dark matter particles. Once this happens, physicists will begin to study the properties of these dark matter particles, and then compare them with the predicted properties of the photon. If the predictions of string theory align with the experimental results for dark matter, this would be a significant argument in favor of physicists being on the right track. Another intriguing possibility involves producing photons in next-generation particle accelerators, the construction of which is currently under discussion. Following the Large Hadron Collider, the Japanese are actually considering funding the International Linear Collider. In this facility, a beam of electrons would be fired along a straight tube, colliding with an opposing beam of anti-electrons. Should the decision be positive, this facility is projected to be built within 12 years. The key advantage of such a collider is its use of electrons rather than protons. Protons, as you know, are composed of 3 quarks held together by gluons. Because of this, proton collisions always tend to be very messy, generating a veritable shower of extraneous particles. An electron, on the other hand, is considered a truly elementary particle. Therefore, its collision with an anti-electron is much cleaner and requires significantly less energy. As a result, with an energy of nearly 250 billion electron volts, such collisions should be capable of producing Higgs bosons. Chinese scientists have expressed interest in constructing a circular electron-positron collider. Work on its creation is tentatively scheduled to begin in 2022 and conclude around 2030. This collider is estimated to cost between $5 and $6 billion. This 100-kilometer circumference device would be capable of reaching energies of 240 billion electron volts. Not to be outdone by their counterparts, physicists at CERN are planning to build a successor to the Large Hadron Collider, known as the Future Circular Collider. Eventually, this facility is projected to achieve energies of 100 trillion electron volts, and its circumference will also be about 100 kilometers. While it remains uncertain whether these accelerators will ever be built, all of this suggests there's hope of discovering dark matter using these next-generation accelerators, following the Large Hadron Collider. Should dark matter particles be found, their characteristics could then be compared with the predictions of string theory. Another prediction of string theory that these accelerators might help verify is the existence of miniature black holes. Since string theory aims to be a theory of everything, it naturally encompasses both gravity and elementary particles. Consequently, physicists anticipate finding tiny black holes within these accelerators. Unlike their stellar counterparts, these miniature black holes are harmless, possessing the energy of tiny elementary particles rather than that of dying stars. In fact, Earth is constantly bombarded by cosmic rays, far more powerful than anything these accelerators could produce, and yet they cause no harmful effects. Furthermore, there's hope we might be able to utilize the greatest accelerator of all time for our research, the Big Bang itself. The radiation from the Big Bang could hold the key to unlocking the mysteries of dark matter and dark energy. First and foremost, the echo or afterglow of the Big Bang is readily detectable. Our satellites are capable of registering this radiation with immense precision. Images reveal that the cosmic microwave background radiation is remarkably smooth, disturbed only by tiny ripples. These ripples in turn reflect the tiny quantum fluctuations that existed at the moment of the Big Bang and were subsequently amplified by it. However, what raises questions is the presence of an irregularity within this relic radiation that we are unable to explain. Some speculate that these are traces of collisions with other universes. Specifically, there's a cold spot, an unusually cold patch on an otherwise uniform background radiation. Some physicists hypothesize that this could be a remnant of some kind of connection or collision between our universe and another parallel universe, which occurred at the dawn of time. If these peculiar markings are indeed found to be evidence of interactions between our universe and parallel universes, then the multiverse theory might well appear more plausible to skeptics. There are already plans to deploy gravitational wave detectors in space, which would allow for more precise calculations. As far back as 1916, Einstein demonstrated that gravity propagates as waves, much like concentric circles radiating outwards when a stone is dropped into a pond. These ripples in spacetime, or gravitational waves, should propagate at the speed of light. However, Einstein hypothesized that they would be so weak that detecting them would likely be impossible in the foreseeable future. He was proven right. It wasn't until 2016, a full century after his prediction, that scientists first succeeded in registering gravitational waves. The colossal LIGO detectors picked up signals from two black holes that had collided in space approximately 1 billion years ago. Each of these detectors, built in the states of Louisiana and Washington, occupies an area of several square kilometers. They are shaped like the letter L, with laser beams directed along each arm. Meeting at the corner of the L, the two beams create an interference pattern so sensitive to vibrations that it was able to detect the faint traces of the black hole collision. For their groundbreaking work, 3 physicists, Rainer Weiss, Kip Thorne, and Barry Barish, were awarded the Nobel Prize in 2017. To achieve even greater sensitivity, there are plans to send gravitational wave detectors into outer space. A new system, known as the Laser Interferometer Space Antenna, or LISA, may be able to detect vibrations originating from the very moment of the Big Bang itself. One proposed configuration for LISA consists of 3 satellites in space, linked by a network of laser beams. Each side of this triangular formation would span approximately 2.5 million kilometers. When a gravitational wave from the Big Bang strikes the detector, it would cause tiny oscillations in the laser beams, which could then be measured by sensitive instruments. The ultimate goal of this program is to record the shock waves of the Big Bang, and then effectively rewind the tape to obtain the best possible understanding of the radiation preceding the Big Bang. These pre-Big Bang waves would then need to be compared with the predictions of various string theory models. This, in turn, might provide quantitative data about the multiverse before the Big Bang. It's even conceivable that with devices even more advanced than LISA, scientists could obtain baby photos of our universe, and perhaps even find evidence of the umbilical cord that connected our nascent universe to its parent universe. One common argument against string theory, for instance, suggests that we actually live in 10 or 11 dimensions. However, there is currently no experimental evidence to support this. But actually, this particular aspect might be testable using existing instruments. Now, if our universe were truly three-dimensional, the gravitational force between objects would decrease inversely proportional to the square of the distance separating them. This famous Newtonian law guides our space probes across billions of kilometers with breathtaking accuracy. In fact, we could, if we wished, guide spacecraft right through Saturn's rings. However, Newton's renowned inverse square law has only been verified over astronomical distances, not in a laboratory setting. The possibility that gravity might not follow the inverse square law at very short distances could in fact indicate the presence of higher dimensions. For example, if the universe had 4 spatial dimensions, gravity would then have to diminish proportionally to the cube of the distance. And if the universe had m spatial dimensions, gravity would diminish proportionally to the m-1 power of the distance between objects. Measuring the gravitational force between 2 objects in a lab, however, is exceedingly rare. Such experiments are inherently challenging because gravitational forces at laboratory scales are incredibly weak. Nevertheless, the first measurements have already been conducted in Colorado, yielding negative results, meaning Newton's inverse square dependence still holds true. Of course, this only means that there are no extra dimensions specifically in Colorado. For theorists, all these criticisms are certainly unwelcome, but they are not necessarily fatal. What truly poses a problem for a theoretician, however, is the prediction of a multiverse, a collection of parallel universes, many of which are far more bizarre than anything a Hollywood screenwriter could ever conjure up. String theory, for example, offers an infinite number of solutions. Each one describes a finite theory of gravity that is completely unlike the one we observe in our own universe. In many of these parallel universes, the proton is unstable. This means all matter simply decays, transforming into a vast cloud of electrons and neutrinos. In such universes, complex matter as we know it, things like atoms and molecules, simply cannot exist. Instead, they contain only a gas of elementary particles. One might argue, of course, that these alternative universes are merely mathematical possibilities, that they are not real. The real problem, however, is that our current theory lacks predictive power. It simply cannot tell us which of these alternative universes are actually real. And in fact, this is not a problem unique to string theory. For instance, How many solutions exist for Newton's or Maxwell's equations? Well, their number is infinite, and it depends entirely on what you are studying. If you start with, say, a light bulb or a laser, and then solve Maxwell's equations, you will find a single, unique solution for each of those devices. But broadly speaking, Maxwell's and Newton's theories also possess an infinite number of solutions, depending on the initial conditions. So, in a sense, we are back to the same situation we started with. It is highly probable that this particular problem is characteristic of any theory of everything. Any such theory will inevitably have an infinite number of solutions, all dependent on the initial conditions. But how exactly do we determine the initial conditions of the entire universe? This essentially means we would have to manually input the Big Bang conditions from outside the theory itself. For many physicists, this feels a bit like cheating. Ideally, we would want the theory itself to tell us the conditions that led to the Big Bang, including the temperature, density, and composition at its very beginning. A true theory of everything should inherently contain its own initial conditions. In other words, we would hope for an unambiguous and precise prediction for the universe's origin. Yet, string theory offers a staggering wealth of choices. Can it predict our universe? Yes, it can. And that is a powerful statement indeed, a goal physicists have pursued for nearly a century. But can it predict just one universe? Probably not. And this, my friends, is what we call the landscape problem. Now, there are a few possible solutions to this problem, though none of them have found widespread acceptance. The first, for example, is the anthropic principle. This principle essentially states that our universe is special simply because we exist within it, conscious beings capable of discussing this very question. In other words, there could be any number of universes out there, but our universe just happens to be the one where conditions make intelligent life possible. The initial conditions of the Big Bang, therefore, were set at the dawn of time in precisely such a way that intelligent life could emerge and exist today. Other universes perhaps might not host intelligent life on a grand scale. The author recalls his first encounter with this concept quite vividly. He remembers his second-grade teacher telling them that God loved Earth so much that he placed it at just the right distance from the sun, not too close so the oceans would not boil, and not too far so they would not freeze. Even as a child, he was astonished by this reasoning, because, in his young mind, it seemed to define the nature of the universe through pure logic. However, today, satellites have discovered more than 4,000 planets orbiting other stars. Sadly, most of them are either too close or too far from their star to support life. So, the teacher's reasoning can be interpreted in two ways. Perhaps there really is a loving God, or perhaps there are thousands of dead planets, situated either too close or too far, and we simply happen to live on the one that is just right for sustaining intelligent life whose representatives can, in fact, debate such profound questions. Similarly, it's plausible to assume that we exist in an ocean of dead universes, and our universe is special simply because we exist within it and are able to ponder such questions. What's more, the anthropic principle helps explain another intriguing, experimentally confirmed fact about our universe. The fundamental physical constants within it are precisely tuned to create the conditions necessary for life to exist. As the physicist Freeman Dyson once wrote, "The universe, it seems, knew we were coming." For instance, if the nuclear force had been just slightly weaker, our sun would never have ignited, and the solar system would have remained dark. Conversely, if the strong nuclear force had been a little stronger, the sun would have burned itself out billions of years ago. So you see, the nuclear force is incredibly precisely tuned. Similarly, if gravity had been a little weaker, the Big Bang might have ended in what's sometimes called a big freeze, leading to a dead, cold, and ever-expanding universe. And if it had been a bit stronger, we might have faced a big crunch, where all life would have been incinerated. However, our gravity is precisely what it needs to be to allow stars and planets to form and to persist long enough for life to emerge. Indeed, we could compile an entire list of these fortunate coincidences that make life possible, and each time we'd find ourselves right in the middle of what's known as the Goldilocks zone, or the habitable zone. So, in essence, the universe is a gigantic lottery, and we've won the jackpot. But according to the multiverse theory, this implies that we coexist with a vast number of dead universes. It's entirely possible that the anthropic principle truly does single out our universe from the millions existing within the cosmic landscape, simply because it harbors intelligent life. Be that as it may, this theory has yet to be fully formulated in its final form, so it's really too early to compare string theory with our current understanding of the universe. One of the fascinating aspects of string theory is that it develops, in a sense, backward, uncovering new mathematics and concepts along the way. Roughly every decade, string theory experiences a revelation that fundamentally changes our perception of its very nature. The author remarked, "I've witnessed 3 such revolutions, Yet, despite this, we still have to fully present string theory in its complete form. We don't yet know its ultimate fundamental principles. Only after those emerge will we be able to compare the theory with experimental results. The author continued, I like to compare the exploration of string theory to a treasure hunt in the Egyptian desert. Imagine one day you stumble upon a small stone jutting out of the sand. You clear the sand from the stone and realize that it's actually the very tip of a colossal pyramid. After years of excavation, you discover peculiar chambers and artifacts within it. Each floor reveals new surprises. Finally, after uncovering many levels, you reach the very last door, ready to open it and discover who built this pyramid. Personally, I believe we haven't even reached the bottom floor yet, because every time we analyze the theory, new mathematical layers keep revealing themselves. We still have many more layers to excavate before we can formulate string theory in its definitive form. In other words, the theory is smarter than we are. String theory, through string field theory, can be expressed by a single equation about an inch long. However, in 10 dimensions, we would actually need 5 such equations. While string theory can be expressed as a field theory, this is still not possible for M-theory. Nevertheless, there's still hope that physicists will one day discover a single unified equation that expresses M-theory. It's widely understood that a membrane, capable of vibrating in a multitude of ways, is inherently very difficult to express in the form of a field theory. Consequently, M-theory comprises dozens of disparate equations that, almost miraculously, describe the very same underlying theory. If we ever manage to write M-theory as a field theory, then in principle it should entirely derive from just one single equation. No one can predict when this might happen, or indeed, if it ever will. However, the public, observing the hype and commotion surrounding string theory, combined with a lack of understandable results, is beginning to show impatience. Even among physicists specializing in string theory, there's a noticeable pessimism regarding its prospects. As Nobel laureate David Gross once put it, string theory is like a mountaintop. As climbers ascend the mountain, the summit is always clearly visible, but it seems to recede as they get closer. The goal is tantalizingly near, yet it invariably slips away from you. The author believes, in my opinion, this is quite natural, because no one knows when or if supersymmetry will ever be detected in a laboratory. However, it's crucial to view the situation from a specific angle. The judgment of a theory's validity or invalidity must rest on concrete results, not on the subjective wishes of physicists. Of course, we'd all love to hope that our cherished theories find confirmation within our lifetimes. This is a deeply human desire, but sometimes nature operates on its own schedule. For instance, the atomic theory found genuine confirmation after 2,000 years, and only recently have scientists gained the ability to obtain realistic images of individual atoms. Even the great theories of Newton and Einstein required decades for many of their predictions to be fully tested and confirmed. The existence of black holes, for example, was predicted by John Michell in 1783, but it wasn't until 2019 that astronomers obtained the first convincing images of their event horizons. I'm personally convinced that the pessimism of many scientists might, in fact, be mistaken. I believe the evidence for our theory won't be found in giant particle accelerators at all. Rather, it will emerge when someone manages to discover the ultimate mathematical formulation for the theory. You see, we might not actually need experimental proof for string theory at all. After all, a theory of everything inherently covers ordinary things as well. If we can derive the mass of quarks and other known elementary particles from the theory's fundamental principles, then that could serve as compelling proof that it is indeed the ultimate theory of everything. The real issue isn't with the experimental successes of the standard model itself. As is well known, there are approximately 20 free parameters that are manually input. These include, for instance, the mass of quarks and the strength of their interactions. We have a wealth of experimental data concerning the masses and interactions of elementary particles. So, if string theory allows us to precisely calculate these fundamental constants based purely on its core principles, without any prior assumptions, then I believe that would definitively prove its correctness. It would truly be a historic event if the known parameters of the universe could be derived from a single elegant equation. But once we have this elusive 1-inch equation, what exactly do we do with it? How do we then address the landscape problem? One theory suggests that many of these potential universes are inherently unstable. They decay and eventually converge towards our familiar universe. Bear in mind that the vacuum isn't simply a boring, featureless void. In fact, it's constantly teeming with universe bubbles, which emerge and disappear much like bubbles in a frothy bath. Stephen Hawking famously referred to this phenomenon as space-time foam. Most of these tiny bubble universes are, indeed, unstable. They suddenly burst forth from the vacuum, only to just as suddenly vanish back into it. This, then, is precisely how something could arise from nothing. Hawking, as we've already discussed, envisioned this as space-time foam, a dynamic froth of countless tiny bubble universes, continually winking into and out of existence from the vacuum. We don't perceive this space-time foam because each individual bubble is far, far smaller than any atom. But every now and then, one of these bubbles doesn't just dissolve back into the vacuum. Instead, it expands, triggering an inflationary process that ultimately gives rise to an entire universe. So this begs the question, why is there something rather than nothing? Well, it's because our universe originally arose from quantum fluctuations within nothingness. Unlike countless other ephemeral bubbles, our universe broke free from the space-time foam and continued its expansion. Did the universe have a beginning? And will our theory of everything provide an answer to the meaning of life? Many years ago, I saw a curious poster put out by a meditation society. It depicted the equations of supergravity in all their mathematical elegance, and from each term, an arrow pointed to a word: peace, serenity, unity, love, and so on. In other words, the meaning of life was apparently embedded within the equation of a theory of everything. Personally, I find it highly unlikely that a mathematical term in any physics equation could be equated with love or happiness. However, I am convinced that a theory of everything will have something profound to say about the meaning of the universe itself. Two great religions, Christianity and Buddhism, hold profoundly different views regarding a creator. In Christianity, God created the world at a specific point in time. Georges Lemaitre, the Catholic theologian and physicist who was one of the architects of the Big Bang theory, believed that Albert Einstein's theory did not contradict the Book of Genesis. In Buddhism, there is no God as such. The universe there has neither beginning nor end. There is only timeless nirvana. So, how can we reconcile these two diametrically opposed viewpoints? The universe either had a beginning or it did not. There are no intermediate options. However, the theory of the multiverse actually allows us to look at this contradiction in a completely new light. Perhaps our universe did indeed have a beginning, as described in the Bible. But it's also possible that Big Bangs are occurring all the time, according to inflationary theory, constantly giving birth to a whole bath of bubble universes. Perhaps these universes are expanding into a much vaster realm, a kind of nirvana of hyperspace. So our universe has a beginning, and it's essentially a three-dimensional bubble floating within a far more expansive 11-dimensional nirvana, where other universes are constantly emerging. Thus, the idea of the multiverse allows us to unite the creationist mythology of Christianity with the nirvana of Buddhism into a single theory, one that is compatible with known physical laws. Ultimately, I am confident that we create our own meaning within the universe. It's far too simple and easy to look to some guru who has descended from mountain heights, bringing us the definitive meaning of the universe. To truly grasp and appreciate the meaning of life, significant effort is required. If meaning were simply handed to us on a silver platter, the very concept of it would be lost. Meaning that is freely given, without effort, would lose its intrinsic value. Everything truly meaningful is earned through struggle and sacrifice, and it is always worth fighting for. But it's difficult to argue that the universe has any inherent meaning if it's ultimately destined to die. In a way, physics has handed the universe a death sentence. Despite all the highly academic discussions about the universe's meaning and purpose, all of it might prove futile. Why? Because our universe is seemingly doomed to perish in what's known as the Big Freeze. According to the second law of thermodynamics, everything within a closed system must eventually decay, rust, or simply fall apart. The natural order of things, you see, is decay, leading eventually to cessation of existence. Everything in existence is inevitably bound to die when the universe itself dies. So, whatever meaning we might ascribe to the universe, its death will ultimately take that meaning with it. However, perhaps the merging of quantum theory with the theory of relativity could offer us a loophole, allowing the universe to survive. As previously mentioned, the second law of thermodynamics dictates that a closed system universe is, sooner or later, doomed to perish. The key word here, of course, is closed. In an open universe, where energy can flow in from the outside, the effects of the second law can actually be reversed. Consider, for instance, a household air conditioner. At first glance, it seems to violate the second law of thermodynamics because it takes in chaotically warm air and cools it down. But an air conditioner receives energy from an external compressor, and therefore, it isn't a closed system. Similarly, life on Earth also appears to defy the second law. I mean, it transforms hamburgers and French fries into a baby in just 9 months, which is quite a miracle if you think about it. So, Why is life on Earth even possible? Well, it's because we have an external energy source, the sun. Earth isn't a closed system, and sunlight allows us to harness the sun's energy, using it to create the food necessary to nourish a baby. So, yes, there is a loophole in the second law of thermodynamics. Sunlight, you see, makes evolution and development from lower to higher forms of life possible. In much the same way, wormholes could potentially be used to open a passage to another universe. Now it appears our universe is indeed a closed one. However, it's not impossible that one day, perhaps in the face of the universe's eventual demise, our descendants will be able to leverage their immense scientific knowledge. They might accumulate enough positive energy to open a tunnel through space and time, and then, using negative energy and the Casimir quantum effect, stabilize it. Eventually, our descendants could master Planck energy. That's the energy at which space and time become unstable, and then use powerful technologies to leave our dying universe. Thus, quantum gravity, instead of merely remaining an exercise in 11-dimensional space-time mathematics, could transform into a cosmic interdimensional lifeboat. This lifeboat would allow intelligent life to bypass the second law of thermodynamics and relocate to a much warmer universe. So, the theory of everything is far more than just a beautiful mathematical theory. In the end, it might very well be our only salvation. The quest for a theory of everything has, in turn, led us to seek the ultimate, unifying symmetry of the universe. All the symmetry we observe around us, from a warm summer breeze to the flaming splendor of a sunset, represents merely a fragment of the symmetry that existed at the dawn of time. That primordial symmetry was broken at the moment of the Big Bang, and now, wherever our gaze admiringly catches the beauty of nature, we are actually seeing its remnants. I like to think that perhaps we resemble the two-dimensional inhabitants of Flatland, living on a mythical plane and utterly incapable of imagining a third dimension, which in their society is considered nothing more than a superstition. At the dawn of time in Flatland, there existed a beautiful three-dimensional crystal. For some reason, this crystal was unstable and shattered into a million fragments, which rained down upon Flatland. For centuries, the Flatlanders tried to reassemble these pieces, fitting them together like a jigsaw puzzle. Eventually, they managed to reconstruct two enormous pieces. One was named the theory of gravity, and the other, quantum theory. However, no matter how hard the Flatlanders tried, they simply couldn't join these two pieces together. Then one day, an enterprising Flatlander put forth a daring hypothesis that made everyone laugh. Why don't we, he proposed, using mathematics as our guide, lift one of the pieces into an imaginary third dimension so that the pieces can finally align and fit together. When this was done, the Flatlanders were astonished to see a sparkling, iridescent gemstone, shimmering with all colors, suddenly appear before them in its perfect and magnificent symmetry. Or, as Stephen Hawking once wrote, if we do discover a complete theory, it should in time be understandable by everyone, not just a few scientists. Then we, as philosophers, scientists, and just ordinary people, will be able to take part in the discussion of the question of why it is that we and the universe exist. If we find the answer to that, it would be the ultimate triumph of human reason, for then we would know the mind of God. And it's at this point that physics ends and metaphysics begins. Physics, you see, tells us nothing about where the physical laws themselves came from. So, St. Thomas Aquinas' cosmological argument, which speaks of a prime mover or a first cause, actually still holds its power today. A key feature of any theory of everything will, in all likelihood, be its inherent symmetry. But where does this symmetry come from? Symmetry, logically, must be a consequence of deep mathematical truths. Yet, where does mathematics itself originate? To this question, our theory of everything also remains silent. The questions raised by that Catholic theologian 800 years ago still remain profoundly significant despite the immense progress we've made in understanding the origin of life and the universe. The universe is a remarkably beautiful, ordered, and simple place. What I find truly astonishing is that all the known laws of the physical universe can be laid out on a single sheet of paper. Of course, that sheet would contain Einstein's theory of relativity. The Standard Model is more complex. Its zoo of elementary particles takes up a significant portion of that page. Together, these can describe everything in our known universe, from what's inside a proton to the farthest reaches of visible space. Given the extreme compactness of this single sheet, it's hard not to conclude that everything was pre-planned, that the universe's elegance reveals the hand of some cosmic designer. For me, this serves as the strongest argument for the existence of God. However, the cornerstone of our understanding of the world around us is science, which is ultimately based on things that are verifiable, reproducible, and falsifiable. That really says it all. In disciplines like literary criticism, things tend to get more complicated over time. Experts are constantly trying to decipher what James Joyce truly meant by this or that passage. Physics, however, moves in the opposite direction. The further we delve, the simpler it becomes, ultimately revealing itself as the consequence of just a handful of equations. I find that quite remarkable. Yet scientists are often reluctant to admit that there might be anything beyond the realm of science. For instance, it's impossible to disprove a negative statement. Imagine we wanted to disprove the existence of unicorns. Even if we meticulously searched most of Earth's surface and found no unicorns, there would always remain the possibility that they live on some undiscovered island or in a secret cave. Therefore, disproving the existence of unicorns is impossible. This means that even 100 years from now, people will still be debating the existence of God and the meaning of the universe. The fact is, these concepts aren't testable, and therefore, they are irresolvable. They lie outside the realm of conventional science. Similarly, even if we've never encountered God during our travels in outer space, there always remains the possibility that God exists somewhere we haven't yet explored. That's why I'm an agnostic. We've only scratched the surface of the universe so far, and it would be overly presumptuous to make sweeping statements about its overall nature, especially aspects beyond the reach of our instruments. It's also worth remembering that any researcher will, sooner or later, have to confront St. Thomas Aquinas' argument for the necessity of a prime mover. In other words, where did everything come from? Even if the universe began exactly as the theory of everything suggests, then where did the theory of everything itself come from? In my view, it exists because it's the only mathematically consistent theory. All other theories inherently possess flaws and contradictions. In my opinion, if you start with any other theory, you can eventually prove that 2 plus 2 equals 5. In other words, these alternative theories are internally inconsistent. Let me remind you that the theory of everything faces numerous hurdles on its path to acceptance. When we introduce quantum corrections into any theory, it typically collapses. It either develops infinite divergences, or its original symmetry is ruined by anomalies. I'm convinced that there's perhaps only one solution for these constraints that can bring the theory into order, effectively ruling out all other possibilities. Our universe cannot exist in 15 dimensions, as such a universe would suffer from fatal flaws. In 10-dimensional string theory, when we calculate quantum corrections, they often contain a factor of open parenthesis d minus 10, close parenthesis, where d represents the dimensionality of spacetime. Evidently, if we set d equal to 10, these troublesome anomalies simply disappear. However, if we equate d to not equal 10, then we get a different universe, one full of contradictions where mathematical logic breaks down. Similarly, when introducing branes and performing calculations within M-theory, we encounter undesirable terms that contain a factor of open parenthesis d minus 11, close parenthesis. Consequently, within string theory, there is only one internally consistent universe where 2 plus 2 equals 4, and it exists in 10 or 11 dimensions. So, this could be a possible answer to the question Einstein posed during his search for a theory of everything. Did God have a choice when creating the universe? Is our universe unique, or are there many forms of its existence? If my line of thinking is correct, then there is no choice at all. There is only one equation capable of describing our universe, because all others are mathematically unsound. Therefore, the final equation of the universe is unique, and while it is unique, its single solution could have an infinite number of manifestations. This sheds light on yet another question. Why is there anything at all in the world rather than simply nothing? In quantum theory, there's no such thing as absolute nothingness. We've seen that absolute blackness doesn't exist, meaning black holes are actually gray and are expected to evaporate. Similarly, when seeking solutions to quantum theory, we find that the minimum energy is not equal to zero. For instance, it's impossible to achieve absolute zero, because even atoms in their lowest quantum energy state still experience fluctuations. Likewise, according to quantum mechanics, it's impossible to achieve zero energy quantum mechanically, as you'll always be left with zero-point energy, which refers to minimal quantum fluctuations. A state of zero fluctuations would violate the uncertainty principle, because zero energy implies a state of zero uncertainty, which is forbidden. So, where did the Big Bang actually come from? Most likely, it was a quantum fluctuation within nothingness. Even nothingness, or pure vacuum, continuously froths with particles of matter and antimatter. These particles spontaneously emerge in pairs from the vacuum, only to disappear back into it moments later. This is precisely how something can arise from nothing. As we've discussed, Stephen Hawking referred to this as space-time foam, envisioning it as a sea of tiny bubble universes constantly popping in and out of existence from the vacuum. We don't perceive this space-time foam because each one of these bubbles is far smaller than any atom. However, every now and then, One of these bubbles doesn't simply dissolve back into the vacuum. Instead, it expands, initiating an inflationary process that ultimately gives rise to an entire universe. So why is there something rather than nothing? Well, it's because our universe originally emerged from quantum fluctuations within nothingness. Unlike countless other bubbles, our universe broke free from the space-time foam and continued to expand. In my opinion, we will need to turn to computers for assistance. This approach, for instance, was adopted when dealing with quark theory. Recall that the Yang-Mills particle acts like a glue, binding quarks together within a proton. Yet, for half a century, no one has been able to rigorously prove this mathematically. What's more, many physicists had practically given up hope that this problem would ever be solved. However, a computer eventually managed to tackle the Yang-Mills equations. This was achieved by approximating spacetime as a sequence of lattice points or nodes. Under normal circumstances, we envision spacetime as a smooth surface with an infinite number of points. As objects move, they traverse this endless continuum, but we can approximate this smooth surface using a lattice or a grid, much like a loosely woven fabric. If we make the distance between these lattice points smaller and smaller, the lattice effectively transforms into continuous spacetime, and the definitive theory begins to emerge. Once the final equation for M-theory is obtained, we will be able to map it onto a lattice and perform calculations on a computer. In such a scenario, the output from a supercomputer would reveal our universe. However, this reminds me of Douglas Adams' science fiction novel, The Hitchhiker's Guide to the Galaxy, where a colossal supercomputer is built with the sole purpose of discovering the meaning of life. After an eternity of computations, that computer concludes that the meaning of the universe is 42. So, it's not inconceivable that the next generation of particle accelerators, or a particle detector deep within a mine, or perhaps even a gravitational wave detector in deep space, might uncover experimental proof for string theory. And if that doesn't happen, then perhaps some ingenious physicist will possess enough persistence and insight to discover the definitive mathematical formulation of a theory of everything. Only then will we be able to compare it with experimental results. It seems physicists can expect many more unexpected twists and turns along the way. However, I'm confident that, in time, we will succeed in finding a theory of everything. But the next question then is, where did string theory itself come from? If there's a grand design embedded within it, then did it have a creator? And if so, does the universe have a purpose and meaning? We've seen how mastering the four fundamental interactions has not only unveiled many of nature's mysteries, but also sparked great scientific revolutions that have profoundly altered the course of civilization itself. By formulating the laws of motion and gravity, Isaac Newton laid the groundwork for the Industrial Revolution. When Michael Faraday and James Clerk Maxwell discovered the unity of electric and magnetic interactions, this, in turn, ignited the electrical revolution. And when Albert Einstein and quantum physicists unveiled the probabilistic and relativistic nature of reality, it ushered in today's high-tech revolution. But now, we may be approaching a theory of everything that will unify all four fundamental interactions. Let's suppose for a moment that we have finally achieved this theory. Let's imagine it has been rigorously tested and universally accepted by scientists worldwide. How would this impact our lives, our thinking, and our understanding of the universe? As for its immediate impact on our daily lives, it would most likely be minimal. Every solution to a theory of everything encompasses an entire universe. Consequently, the energy at which this theory becomes relevant is the Planck energy, which is a quadrillion times greater than the energy achieved in the Large Hadron Collider. The energy scale of a theory of everything corresponds to the birth of the universe and the mysteries of black holes, not to your everyday concerns or mine. The real impact of such a theory on our lives, however, would likely be philosophical, as it would be expected to answer profound questions that have vexed generations of great thinkers. Is time travel possible? What existed before the creation of the world? And where did the universe come from in the first place? As the great biologist Thomas Huxley remarked in 1863, the question of questions for mankind, the problem which underlies all others and is more interesting than any of them, is to determine man's place in nature and his relation to the cosmos. This, however, still leaves us with an open question. What can a theory of everything truly tell us once it fully comprehends the universe? Albert Einstein's secretary, Helen Dukas, once recalled that Einstein was simply inundated with letters, all asking him to explain the meaning of life and whether he believed in God. He often said he couldn't possibly answer all these questions about the universe's purpose. These profound questions about the meaning of the universe and the existence of a creator still, to this day, captivate the public imagination. By the year 2018, a private letter written by Einstein shortly before his death was put up for auction. Surprisingly enough, the winning bid for this so-called God letter reached $2.9 million, far exceeding the auction house's expectations. In this and other letters, Einstein often lamented his inability to answer questions about the meaning of life, but he expressed his thoughts on God quite clearly. One problem, he wrote, is that there are actually two types of gods, and we often confuse the two. Firstly, there's a personal God, the God you pray to, the God of the Bible, who punishes or incentivizes and rewards believers. Einstein did not believe in this God. He didn't believe that the God who created the universe would intervene in the affairs of mere mortals. However, Einstein did believe in Spinoza's God. That is to say, a God of order within the universe, one that is beautiful, simple, and elegant. The universe could have been ugly, random, and chaotic, but instead there exists a hidden order within it, a structure that is mysterious yet profound. As an analogy, Einstein once said he felt like a child who had entered a vast library. Everywhere there were stacks of books containing the answers to the universe's mysteries. His life's goal, in fact, was to try and read at least a few chapters from these books. However, he left one question open. If the universe is like a vast library, is there a librarian? Or is there someone who wrote these books? In other words, if all physical laws can be explained by a theory of everything, then where did its foundational equation come from? Additionally, another question that plagued Einstein was whether God had a choice when creating the universe. These questions, however, aren't quite so clear-cut when we try to use logic to prove or disprove the existence of God. Stephen Hawking, for instance, did not believe in God. He wrote that the Big Bang happened in an instant, so God simply didn't have time to create the universe as we see it. In Einstein's original theory, the universe expanded almost instantaneously. But in the multiverse theory, our universe is nothing more than a bubble, coexisting with other bubble universes that are constantly emerging. If that's the case, then perhaps time didn't suddenly emerge with the Big Bang but existed even before our universe began. Each universe is born in a brief instant, but it's not impossible that the entire collection of universes in the multiverse is eternal. So, the theory of everything leaves the question of God's existence open. Meanwhile, for centuries, theologians have tried to do the opposite, to prove God's existence using logic. St. Thomas Aquinas, the great 13th century Catholic theologian, proposed 5 famous proofs for the existence of God. These proofs are interesting because even today, they raise profound questions relevant to the theory of everything. 2 of them are actually redundant and duplicate the others, so Aquinas' proofs can effectively be reduced to 3 main points. Firstly, there's the cosmological argument. Objects move because they are pushed, meaning something sets them in motion. But what was the prime mover, or the first cause that initiated the universe? Well, it must be God. Secondly, we have the teleological argument. Everywhere around us, we see objects of immense complexity and ingenuity. However, every design, at some point, requires a designer. Therefore, the first designer must have been God. Thirdly, there's the ontological argument. God, by definition, is the most perfect conceivable being. However, it's also possible to imagine that God does not exist. But if God did not exist, then by that very definition, he couldn't be perfect. Therefore, he must exist. These proofs for God's existence remained unchallenged for many centuries, until, in the 19th century, Immanuel Kant found a flaw in the ontological argument. He argued that perfection and existence, after all, are 2 different categories. Perfection does not necessarily imply existence. However, the other 2 arguments need to be re-examined in light of modern science and the theory of everything. Now, the analysis of the teleological argument is quite straightforward. Everywhere we look, there are objects of extraordinary complexity. However, the ingenuity of the life forms around us can be explained by evolution. Given enough time, pure chance can drive evolution through the survival of the fittest. So, more complex structures randomly emerge from simpler ones. Life, therefore, does not require a prime designer. The analysis of the cosmological argument, however, is not as clear-cut. Today, physicists can effectively run the video backward and show that the universe began with the Big Bang, which initiated all motion. However, to go back even further in time, to the era before the Big Bang, we have to use the multiverse theory. But even if we assume that the multiverse theory explains where the Big Bang came from, we then have to ask the next question. Where did the multiverse itself come from? Finally, if we say that the multiverse is a logical consequence of a theory of everything, then we're forced to ask, where did the theory of everything itself come from? This is where physics stops and metaphysics begins. Physics by its very nature doesn't tell us where the physical laws themselves come from. So, the cosmological argument of St. Thomas Aquinas, which speaks of a prime mover or a first cause, still holds its power today. A key characteristic of any theory of everything will, in all likelihood, be its inherent symmetry. But where does this symmetry come from? Symmetry must be a consequence of profound mathematical truths. But then, where does mathematics itself come from? Our theory of everything also remains silent on this question. The questions raised by that Catholic theologian 800 years ago are still profoundly relevant, despite immense progress in our understanding of the origin of life and the universe. The universe is a remarkably beautiful, ordered, and simple place. I find it utterly astonishing that all the known laws of the physical universe can be written down on a single sheet of paper. Naturally, this sheet would include Einstein's theory of relativity. The Standard Model is more complex. Its zoo of elementary particles takes up a significant portion of that sheet. Together, these theories can describe everything in our known universe, from what's inside a proton to the most distant reaches of visible space. Given the extreme compactness of this single sheet of paper, it's difficult not to conclude that everything was planned in advance, that the elegance of the universe reveals the hand of some cosmic designer. For me, this serves as the strongest argument for the existence of God. However, the cornerstone of our understanding of the world around us is science, which is ultimately based on things that are verifiable, reproducible, and falsifiable. And that essentially says it all. In disciplines like literary studies, things tend to get more complicated over time. Experts are constantly debating what James Joyce truly meant by this or that passage. Physics, however, moves in the opposite direction. The further we delve, the simpler it becomes, ultimately revealing itself to be a consequence of just a handful of equations. I find that absolutely remarkable. Yet, scientists are often reluctant to admit that there might be things in the world beyond the realm of science. For instance, it's impossible to disprove a negative assertion. Imagine we wanted to disprove the existence of unicorns. Even if we scoured most of the Earth's surface and found no unicorns, there would always remain the possibility that they live on some undiscovered island or in a secret cave. Thus, disproving the existence of unicorns is, in fact, impossible. This means that even 100 years from now, people will still be debating the existence of God and the meaning of the universe. The point is, these concepts are not testable and therefore irresolvable. They lie outside the realm of conventional science. Similarly, even if we've never encountered God during our travels through deep space, the possibility of His existence somewhere we haven't yet explored always remains. That's why I'm an agnostic. We've only scratched the surface of the universe so far, and it would be overly presumptuous to make sweeping statements about its overall nature, especially aspects currently beyond the reach of our instruments. We also shouldn't forget that any researcher will, sooner or later, have to confront St. Thomas Aquinas' thesis on the necessity of a prime mover. In other words, where did everything come from? Even if the universe began exactly as the theory of everything suggests, then where did the theory of everything itself come from? In my view, it exists because it's the only mathematically consistent theory. All other theories inherently possess flaws and contradictions. In my opinion, if you start with any other theory, you can ultimately prove that 2 + 2 = 5. In other words, these alternative theories are internally inconsistent. I should remind you that the theory of everything faces numerous obstacles on its path to acceptance. When we introduce quantum corrections into any theory, it typically breaks down. Infinite divergences arise, or its original symmetry is destroyed by anomalies. I am convinced that there is perhaps only one solution for these given constraints, one that can bring the theory into order, thereby ruling out all other possibilities. Our universe cannot exist in 15 dimensions, because such a universe would suffer from fatal flaws. In 10-dimensional string theory, when we calculate quantum corrections, they often contain a factor of open parenthesis d minus 10, close parenthesis, where d represents the dimensionality of space-time. Evidently, if we take d to be equal to 10, then these troublesome anomalies disappear. However, if d is not equal to 10, we would then get a different universe, one full of contradictions where mathematical logic breaks down. Similarly, when introducing branes and performing calculations within M-theory, we encounter undesirable terms containing the factor open parenthesis d minus 11 close parenthesis. Therefore, within the framework of string theory, there exists only one internally consistent universe, one where 2 + 2 = 4, and it exists in either 10 or 11 dimensions. So, this offers a possible answer to the question Einstein posed during his search for a theory of everything. Did God have a choice when creating the universe? Is our universe unique, or are there many forms of its existence? If my ideas are correct, then there is no choice at all. There is only one equation capable of describing our universe, because all others are mathematically unsound. So, the universe's final equation is unique, and this single, unique solution can encompass an infinite range of possibilities. This brings us to another fundamental question. Why is there something rather than nothing at all in the universe? Well, in quantum theory, there is no such thing as absolute nothingness. We've previously discussed how absolute blackness doesn't truly exist, implying that black holes are, in fact, gray and should eventually evaporate. Similarly, when we look for solutions in quantum theory, we find that the minimum energy is never zero. For instance, it's impossible to achieve absolute zero, because even atoms in their lowest quantum energy state still experience fluctuations. Likewise, according to quantum mechanics, achieving zero energy is quantum mechanically impossible. You will always be left with zero-point energy, which means minimal quantum fluctuations. A state of zero fluctuations would, in fact, violate the uncertainty principle. This is because zero energy would imply a state of zero uncertainty, which is forbidden. So, where did the Big Bang come from? Most likely, it was a quantum fluctuation within nothingness. Even nothingness, or pure vacuum, continuously seethes with particles of matter and antimatter. These particles spontaneously appear in pairs within the vacuum and then disappear back into it. This is precisely how something could emerge from nothing. As we've mentioned before, Stephen Hawking referred to this as space-time foam. He envisioned it as a foam of tiny bubble universes constantly popping out of and disappearing back into the vacuum. We don't observe this space-time foam because each bubble is far smaller than any atom, but every now and then, one of these bubbles doesn't just dissolve back into the vacuum. Instead, it expands until an inflationary process begins, giving rise to an entire universe. So, why is there something rather than nothing? Well, it's because our universe originally emerged from quantum fluctuations within nothingness. Unlike countless other bubbles, our universe broke free from the space-time foam and continued to expand. Did the universe have a beginning? Will our theory of everything provide an answer to the meaning of life? Many years ago, I saw a rather peculiar poster produced by a meditation society. It depicted the equations of supergravity in all their mathematical beauty, and from each term, an arrow pointed to words like peace, tranquility, unity, love, and so on. In other words, the meaning of life was seemingly embedded directly within the equation of the theory of everything. Personally, I find it highly unlikely that a mathematical term in any physics equation could be equated with love or happiness. However, I am convinced that the theory of everything will indeed have something significant to say about the universe's meaning. Two great religions, Christianity and Buddhism, hold opposing views regarding a creator. In Christianity, God created the world at a specific point in time. Georges Lemaitre, a Catholic theologian and physicist, and one of the architects of the Big Bang theory, believed that Einstein's theory did not contradict the Book of Genesis. In Buddhism, however, there is no God as such. The universe there has neither a beginning nor an end. Instead, there is only timeless nirvana. How can we reconcile these two diametrically opposed viewpoints? The universe either had a beginning or it didn't. There are no intermediate options. But in fact, the multiverse theory offers us a completely new perspective on this contradiction. Perhaps our universe did have a beginning, as suggested in the Bible. However, it's also possible that Big Bangs are constantly occurring, according to inflationary theory, spawning a whole bath of bubble universes. These universes might be expanding within a much vaster region, a kind of nirvana of hyperspace. So, our universe does have a beginning, and it exists as a three-dimensional bubble floating in a much vaster 11-dimensional nirvana, where other universes are constantly emerging. In this way, the idea of the multiverse allows us to connect the creationist mythology of Christianity with the nirvana of Buddhism into a single theory that is compatible with known physical laws. Ultimately, I believe we create our own meaning within the universe. It's far too easy and simplistic to look to some guru descended from mountain heights to hand us the universe's meaning. To truly understand and appreciate the meaning of life, effort is required. If meaning is simply handed to us ready-made, the very concept loses its essence. A meaning of life freely given would lose its profound significance. Anything truly meaningful is forged through struggle and sacrifice, and it is undoubtedly worth fighting for. However, it's difficult to argue that the universe has meaning if it is destined to die someday. In a way, physics has pronounced a death sentence upon the universe. Despite all the highly academic discussions about the universe's meaning and purpose, all of it might prove futile. This is because our universe is, in fact, doomed to perish in what's known as the Big Freeze. According to the second law of thermodynamics, everything in a closed system must eventually decay, rust, or fall apart. The natural order of things is decay and, ultimately, the cessation of existence. Everything in the world must inevitably die when the universe itself dies. So, whatever meaning we might ascribe to the universe, its eventual death will take that meaning with it. But then again, perhaps the merger of quantum theory with the theory of relativity might just offer us a loophole, allowing the universe to survive. As we've discussed before, the second law of thermodynamics states that, eventually, any closed system, and by extension, the universe, if it were truly closed, is destined for ultimate demise. The key phrase here, of course, is closed system. In an open universe, however, where energy can flow in from an external source, the effects of the second law can actually be reversed. For instance, a household air conditioner might appear, at first glance, to violate the second law of thermodynamics. After all, it takes in chaotically warm air and cools it down. But of course, the air conditioner receives energy from an external compressor, and thus, it's not a closed system. Similarly, life on Earth also seems to defy the second law. I mean, think about it. In just 9 months, it transforms hamburgers and French fries into a baby. That's quite a miracle, isn't it? So, why is life on Earth even possible then? Well, it's because we have an external energy source, the sun. Earth isn't a closed system, and sunlight allows us to harness the sun's energy to produce the food vital for nourishing that baby. So there really is a loophole in the second law of thermodynamics. Sunlight, in fact, makes evolution and the development from lower to higher life forms possible. In the same vein, we could potentially use wormholes to open a passage to another universe. Now, it appears our universe is in fact a closed system, but it's not impossible that one day, perhaps faced with the universe's ultimate demise, our descendants will possess the immense scientific knowledge needed to accumulate enough positive energy and open a tunnel through space and time. They might then stabilize it using negative energy and the Casimir effect. Eventually, our descendants may master Planck energy. That's the energy at which space and time themselves become unstable. They could then use powerful technologies to escape our dying universe. So, instead of merely being an exercise in the mathematics of 11-dimensional space-time, quantum gravity would essentially become a cosmic, interdimensional lifeboat. This lifeboat would allow intelligent life to circumvent the second law of thermodynamics and relocate to a much warmer universe. Therefore, the theory of everything is far more than just a beautiful mathematical construct. Ultimately, it could well be our only salvation. The quest for a theory of everything has, in essence, led us to seek the universe's ultimate, unifying symmetry. All the symmetry we observe around us, from the gentle summer breeze to the blazing splendor of a sunset, is merely a fragment of the symmetry that existed at the very dawn of time. That primordial symmetry was broken at the moment of the Big Bang, and now, wherever our eyes rapturously catch the beauty of nature, we are seeing its remnants. I like to think that we might, perhaps, resemble the 2D inhabitants of Flatland, living on a mythical plane and utterly incapable of imagining a third dimension, which, in their society, is simply considered a superstition. At the dawn of time in Flatland, there existed a beautiful three-dimensional crystal. For some reason, it was unstable and shattered into 1 million fragments, which then rained down upon Flatland. For many centuries, the inhabitants of Flatland tried to reassemble these pieces, fitting them together like a jigsaw puzzle. Eventually, they managed to reconstruct 2 gigantic pieces. One was called the theory of gravity, and the other, quantum theory. However, no matter how hard the Flatlanders tried, they simply couldn't unite these 2 pieces. Then, one day, an enterprising Flatlander put forth a daring hypothesis that made everyone laugh. He asked, "Why don't we, by relying on mathematics, lift one of the pieces into an imaginary third dimension so that the pieces align and fit perfectly together?" And when this was done, the Flatlanders were astonished to see a sparkling iridescent jewel, shimmering with all colors, suddenly appear before them in its perfect and magnificent symmetry. Or, as Stephen Hawking once wrote, "If we do discover a complete theory, it should in time be understandable by everyone, not just a few scientists. Then we shall all, philosophers, scientists, and just ordinary people, be able to take part in the discussion of the question of why it is that we and the universe exist. The answer to that question will be the complete triumph of human reason, for then we will know the mind of God."